that favorite number without having to triage the entire array. There's another data structure called a mapping. So let's create this new data structure. So this data structure is going to be of type mapping. A mapping takes some type of key and spits out whatever variable it's mapped to. So in this case, if we're saying we want to use the name Becca to find her favorite number, we would say the string Becca is going to be mapped to the uint 256 favorite number. And similar to all the other variable declarations, the first part is going to be the typing. So this is going to be a type mapping of string mapped to uint 256. We're going to give this public visibility, and we'll call it name to favorite number. And without adding any other functions that work with it, if we deploy this, we can see we have this blue button because we're not making a state change, name to favorite number. And if we type in Becca in here, obviously nothing's going to happen because we haven't added this mapping in yet. So in our add person down here, let's even have this add person also add to the mapping. So we can do name to favorite number. And then the key is going to be this name. So of Becca, we're going to say we're going to map the name Becca to the favorite number. Now we're going to go ahead and compile. Again, I'm hitting Command S. Deploy. We can scroll down here. If we look up Becca in here, we're going to get nothing. However, if we add Becca and her favorite number being 24, this add person is going to add it both to the array and to this mapping. Now, if we look up name to favorite number, we see that Becca returns 24. Now, one other thing I want to show you guys, just because compilers are going to yell at you if you don't have them, is typically at the top of these contracts, you'll want to add an SPX license identifier. Basically, Solidity and the Ethereum community found out that trust in a smart contract can be better established if source code is available. And in terms of legality and copyright, it just makes life a lot easier if you add that license identifier right at the top of your Solidity. We're going to use the MIT license identifier because it's the most open license out there. It means, hey, anybody can use this code and we don't care. So you'll see a majority of Solidity contracts have this SPX license identifier, MIT at the top, and compilers will yell at you a lot less. Awesome. We now have a contract that we've decided that we liked. It's got mappings. It enables us to actually store people and their favorite numbers. This is fantastic. We've done all of our testing in this JavaScript VM, and we've decided, you know what? We want to deploy this to an actual testnet or an actual mainnet. How do we actually deploy this so that other people can interact with this contract? We are again going to use Rinkeby because that's what we use to make our first transaction. Now, again, you will need some type of test Ethereum in your testnet wallet. So again, if you get lost, you can always just Google Rinkeby faucet or Rinkeby testnet faucet and find a faucet. Or a better alternative would be to come to the link token contracts in the Chainlink documentation at docs.chain.link and scroll down or just look up Rinkeby. This link token contracts page has the most up-to-date faucets for any testnet that it supports. So for example, we get a testnet ETH faucet right here, which also just happens to be that exact faucet that we used earlier. The only thing you need to change in Remix is we need to change from JavaScript VM to injected Web3. And MetaMask will actually pop up and say, hey, would you like to connect to this application? Anytime you're working with a Web3 application or a web application that wants to access your funds or work with your MetaMask, MetaMask will pop up and ask for authorization first. This is really good so that we know which applications we're actually connected to. So we're going to go ahead and say next, connect, and we can see here that we've even connected here and that our account on the main network has 0 ETH. And Remix even tells us, hey, you're on the main network. So let's go ahead and switch to the Rinkeby network. And we can now see we're on the Rinkeby network and we have 17.74 ETH on this Rinkeby test network. Injected Web3 means we're taking our MetaMask and injecting it into the source code of the browser here. And that's the difference between injected Web3 and JavaScript VM. Web3 provider is if we want to use our own blockchain node or our own Web3 provider. When we do injected Web3, we're saying our Web3 provider is our MetaMask, which will work perfectly for what we're trying to do. So since we already have some tests on Ethereum, let's go ahead and deploy this and see what this would actually look like if we deploy to a mainnet. The process is going to be exactly the same, right? The only difference is we would be on the mainnet instead of Rinkeby. So let's go ahead, hit deploy. We'll uncheck published IPFS, hit deploy. MetaMask will pop up asking if we want to do this transaction, because remember, we are deploying a contract. We are changing the state of the blockchain. So we have to pay a little bit of gas fee for it. So we're going to go ahead and hit confirm. And we get a link to Rinkeby Etherscan, similar exactly as we saw before when we made a transaction. The difference here is that instead of sending Ethereum to somebody, we're actually making a transaction on the blockchain to create a contract. After a short while, it will show up here on Etherscan with a success, the number of block confirmations, which again is the number of blocks appended to the block that included our transaction. We see from, which is our account here, and we see to is this new contract that we just created. And we can even click it, and we see that there's this unique transaction hash that created a new smart contract. And same as working with the VM, we have all the exact same functions in here. And you can see if I hit retrieve, these three functions, since they're not making a state change, you can just click them and no transactions will be made. However, what do you think is going to happen if I hit store? If you guessed MetaMask will pop up, you guessed correctly. Again, we see the familiar pieces here. We have a gas price, gas limit. Go ahead and hit confirm. We get another transaction here. And once this transaction goes through, we should be able to call our retrieve function and see a new number. If we call it now, nothing shows up because our original transaction hasn't succeeded. But I bet if we look at it now, okay, it's still indexing, but it looks like it's been included. If we hit it now, we do indeed see this value here. And we can do the same thing with adding a person. We'll add Becca. We'll say her favorite number is 24. MetaMask will pop up. We'll go ahead and confirm the transaction. And if I look up Becca and the name to favorite string right now, it's going to show nothing because our transaction hasn't gone through yet. But if we wait a little bit, I should probably spell her name right, we do see 24. And if we look at the 0th index, we also see Becca's been added here as well. Now, all this Solidity code that we wrote, and when we interacted with this blockchain here, all this Solidity was compiled down to the EVM, also known as the Ethereum Virtual Machine. A lot of the blockchains out there today are what's called EVM compatible. And that means that all this Solidity and all these functions that we're creating can still compile down to EVM and deployed on their blockchain. You'll find out a little later when we look to work on a non-Ethereum based chain that we can still deploy our Solidity smart contracts to these other chains as well. But that's a term you'll hear more and more, the Ethereum Virtual Machine, or EVM. Now, take a break, give yourself a high five because you just deployed your first smart contract and you learned the basics, the fundamentals of Solidity. So huge congratulations on how far you've gotten. Now, in our second projects, we're going to take the fundamentals a step further and start going into the more of the intricacies of Solidity. But just as a quick recap, the first thing you always got to do in your smart contracts is name the Solidity version. Then you'll have to name your contract. A contract in Solidity is like a class and defines all the functions and parameters of your contract. There's many different types in Solidity, like unsigned integer, 256, Boolean, and bytes. We can create structs in Solidity. We can create arrays in Solidity. We can create mappings in Solidity. We can create functions in Solidity. View functions don't make a state change. Memory and storage are two different ways to initialize where a variable is going to be saved. All the Solidity code that we're working with gets compiled down to the Ethereum Virtual Machine. And last but not least, congratulations on taking your first step in learning Solidity. Let's move on to the next project. All the code, tips, and links that we're going to be working with can be found in our course repository. We can scroll down to Lesson 2, Storage Factory, click it here, and we can see all the code we're going to be working with. Good luck. All right, so we've done it. We've got our first contract out of the way. We're understanding some of the basics of Solidity. Now let's move onward. Let's get a little bit more advanced with what we're going to do with our smart contracts. And let's build what's called the factory pattern of smart contracts. So we have our simple storage contract here, which is great. It allows us to store numbers and store favorite numbers associated with different people, and this is great. What if, though, I want to have a lot of these simple storage contracts deployed? I want to give people the ability to generate and deploy their own lists based off of this contract. This is where the factory pattern comes into play. So let's go ahead and create a new contract. So in this contracts folder, I'm going to do new file. We're going to call this storage factory.sol. And now we'll have a storage factory.sol. Now, the way that we're going to do this is that you need simple storage and storage factory in the same folder. I have both of them in this contracts folder, but if you have them outside or in a different folder, that's okay. Just make sure wherever they are, they're in the exact same folder. So let's figure out how to get a contract to actually deploy another contract. We're going to add those basic pieces that we added in that simple storage.sol. We'll add the SPDX license identifier, which will be MIT. We'll choose our Solidity version, which will be Pragma Solidity. And we'll say anything in the 6 range. And then we'll create our contract. We'll say contract storage factory, and we'll create our brackets here. And I'm going to do Command S or compile, whatever you want to do. Things are looking good here. Great. So how can this contract deploy a simple storage contract? Well, the first thing that we're going to need to do is actually import this simple storage into our storage factory contract. We need to import it so that our storage factory contract knows what a simple storage contract even looks like. The way that we can import it is by doing the command import and then the file path that the simple storage is located. So the file path for this is going to be at /simple storage.sol. This means that simple storage is in the exact same directory as storage factory. Doing this line is equivalent to copying everything in this contract bit, coming over to storage factory and pasting it above. You can even save and compile and have 2 contracts in the same file. Now, what's interesting about having 2 contracts in the same file is that when you go to deploy, you'll actually have a choice of which one you want to deploy. And it's the same thing if I do that import statement. So if I delete all this and I go back to import./simple storage.sol, in our deploy tab still, you'll see that we still have our choice of which contract we actually want to deploy. So this is how we actually import a contract or import any type of file that we want so that our contract knows what that contract looks like and can do. So if we want this contract to then be able to deploy a simple storage contract, we're of course going to have to create a function that can do that. So we'll do function. We'll call it create simple storage contract. We'll make this a public function. We'll do our little open and close bracket in here. The way we can generate a contract of simple storage type is by using a new keyword. So let's create a simple storage variable. We'll say a variable of type simple storage contract. We'll name this variable simple storage with a lowercase s equals new simple storage. What this line is saying is we're going to create an object of type simple storage contract. We're going to name it simple storage with a lowercase s. And we're going to say this is going to be a new simple storage contract. And we're saying this simple storage contract takes no input parameters. Of course, if we deploy this contract as is by going to our deploy tab, choosing the storage factory, staying on a JavaScript VM, deploying, scrolling down, we have this function that doesn't return anything. So we're creating new contracts, but we can't really read where those contracts are being created. We'd have to look on a block explorer like Etherscan or something. So let's make a way for us to keep track of all the different simple storage contracts that we deploy. Let's put them in a list or in an array. So what we can do is we can say simple storage array of visibility public, and we'll call it simple storage array. We'll initialize this simple storage array. And every time we deploy, we create one of these new simple storage contracts, we'll add it to our simple storage array. So we'll do simple storage array dot push, and we'll push this simple storage variable. So again, I'm compiling or hitting Command S, delete that most recent contract. We'll choose the storage factory and not the simple storage, and we'll hit deploy. Now, if we scroll down to our storage factory, we have this blue button, which stands for our simple storage array. If we try to see what's at index 0, we get an error, of course, because we haven't added anything to it yet. If I click this create simple storage contract orange button here, now I've created a transaction that's going to create a new simple storage contract and push it onto our simple storage array. Now, if I try to access the 0th index or the first index of this array, I'm going to get this address here. This is the address that this simple storage contract was deployed to. So we've successfully deployed a contract to the blockchain from another contract. And this, of course, is really exciting. Now, we can actually do more than just deploy the contracts. We can actually deploy contracts from another contract and then call those functions as well. So let's create a new function where we call this store function, and we'll also create a function where we call the retrieve function from our storage factory. So we'll do function storage factory store. We're going to shorthand it by saying SF store. We'll have it take uint256 simple storage index and a uint256 underscore simple storage number. We'll make this a public variable as well in our little brackets here. And the reason I'm choosing a simple storage index is because we're going to choose which simple storage contract in our list that we want to interact with. And then we're also going to pass a simple storage number to call on the store function, which of course we need to pass a favorite number to. Anytime that you interact with a contract, you need two things. You need the address of the contract you want to interact with, and you also need the ABI. For us, we figured out that we're going to push and get this address from this simple storage array. We can get the ABI, or the application binary interface, from this import. We'll explain the application binary interface a little bit more later. For now, just know that in order for us to interact with this simple storage contract, we can just do simple storage, and then we'll pass this simple storage the address of that simple storage contract. To get the address of that simple storage contract, we'll say grab the address inside the simple storage array at index simple storage index. This will return that contract that we want to interact with. So we could even say simple storage equals simple storage at that address in the array. Once we get this contract, we can then call any and all of its functions. So we could call simple storage dot store this simple storage number. Now, if we compile this, we go to our deploy tab, deploy the factory, hit deploy, open this up, we can see we have a couple different functions here. We, of course, have our create simple storage function, which creates the contract and adds it to our array. We now have this SF store, which stores a number to one of those contracts on this array. And then we have a lens into that simple storage contract. So if I create a simple storage contract, I can now store on that 0th contract, on that first contract, any number that I want, like 55. Of course, I can't really see that 55 because we didn't add a retrieve functionality. We didn't add a way to actually listen or read or retrieve that favorite number that we got. So let's add that now. So we'll create a new function called sfget, and this will take a uint 256 simple storage index and as a parameter, and we'll choose one of these contracts on this array and return its favorite number, calling the retrieve function on that contract. So since we're just going to be reading state, this can be a public view function that will return a uint 256. To do this, we need to access that contract once again. So we'll say simple storage equals simple storage at that address of simple storage array at index underscore simple storage index, and call, and we can return simple storage dot, we call this retrieve function. I'm just going to copy paste it so I don't spell it wrong. Simple storage, we'll put the semicolon here too, and here. Now, if we compile this, go to our deploy tab, delete the most recent, choose the storage factory, and hit deploy, we can see we now have an sfget function. So let's go ahead, create a simple storage contract. We'll store a function on the 0th contract. We'll store 55 as its favorite number, and we'll hit that. And then for sfget, we'll see if we can get the favorite number of the 0th contract. And we do indeed get 55. Awesome. We can actually even refactor this code to be a little bit simpler here. We don't need to save this simple storage contract as a variable here. We can actually just call retrieve on this whole section here, paste retrieve at the end, and just return like this. The same goes for our sf store. We can delete, saving it as a variable. We can copy this dot store, paste it at the end here, and delete this as well. Now we'll compile, delete the most recent, we'll deploy the storage factory. And if we go into it, create a simple storage, store the number of 55, see what's at the 0th index, and we do indeed see 55. So this is really cool. This is a way for us to actually deploy contracts and interact with contracts from another contract. Now, to deploy a contract, we do need all the functionality of that contract imported. However, to interact with a contract, we don't need all of the functionality. We'll learn about interfaces in the next lesson, which will allow us to actually interact with a contract without having all of the functions defined. And now I'm going to show you something really cool. Simple storage has got a lot of really cool functions, and maybe I want all these functions inside my storage factory. I want my storage factory to be able to create simple storage contracts, and I want it to be a simple storage contract itself. Well, what I can do is my storage factory can actually inherit all the functions of simple storage without me having to copy paste all these functions and all these variables over to storage factory. What I can do is I can do Solidity's version of inheritance. I can say contract storage factory is of type simple storage, or is of contract simple storage. And just by doing this line right here, my storage factory contract now we'll have all of the functions and variables of simple storage. So it'll have a store function, a retrieve function, an add person function, a people array, a name to favorite number mapping. It'll have everything because I will inherit it with this is syntax. So if I go to my deploy tab now, let's look at what our last storage factory was. All we did to change this was add is simple storage. And we can see just the 4 functions that we originally added. If I delete this now, if I save and compile the storage factory, let's go ahead and deploy storage factory. If we open this up now, we can see not only do we have all the functions originally defined in our storage factory, but we additionally have all the functions from our simple storage. And awesome, you've completed the second lesson. We've learned about some incredibly powerful tools here. We've learned how to import entire chunks of code from other files into our files. We've learned how to do inheritance. We've learned how to deploy contracts from our contract. And then we've learned how to interact with different contracts from outside of our contract. Well done. Now is a great time to take a breath, take a breather, and review what you've learned. The GitHub repository associated with this course also has all the code for this lesson. So let's jump into it. So we're back in Remix now, and we're going to go to contracts, and same as before, we're going to create a new file. We're going to call this fundme.sol. Now, same as last time, we're actually going to add this SPDX license identifier, MIT right at the top, and then we're going to choose our Solidity version. So we're going to go pragma, Solidity, and for this, we're just going to do greater than or equals to 0.6.6 and less than 0.9.0. And great. This should look pretty familiar. Now, we're going to do contract fundme, and we're going to start working. So what again do we want this contract to do? We want this contract to be able to accept some type of payment. So let's create a new function that can accept payment. We'll call it fund. So we'll do function, fund, public, and we'll add a new keyword in here called payable. When we define a function as payable, we're saying, hey, this function can be used to pay for things. When you call a function, every single function call has an associated value with it. Whenever you make a transaction, you can always append a value. This value is how much way or gwei or fini or ether you're going to send with your function call or your transaction. As we mentioned before, way, gwei, and ether are just different ways to talk about how much ether you're going to send. So if we look at a way to Ethereum converter, 1 ETH is this much way. 1 way is the smallest denomination of ether. You can't break up Ethereum into anything smaller than 1 way. This is why when you're talking about how much something costs, everything always defaults to way, or the smallest unit of measure in Ethereum. So again, for us to test, we're going to stick with the JavaScript VM for now. If we hit deploy, we get a new contract, and this button is now red. It's red because it is a payable function. So now if I hit this fund button, I can add a value associated with it. So what do we want to do with this funding? What do we want to do when people send us something? Well, let's keep track of who sent us some funding. So what we can do is we can create a new mapping between addresses and value. So let's do a mapping of address to uint256, which will represent the value. We'll make this a public mapping, and we'll call it address to amount funded. Now, in this fund function, let's keep track of all the people who sent us money, or all the addresses that sent us some value. To do this, we can use some keywords that go along with every transaction. So we'll say address to amount funded of message.sender equals or plus equals message.value. Message.sender and message.value are keywords in every contract call and every transaction. Message.sender is the sender of the function call, and message.value is how much they sent. So whenever we call fund now, somebody can send some value because it's payable, and we're going to save everything in this address to amount funded mapping. So if we deploy this now in our JavaScript VM, we now have, again, a new view function called address to amount funded, and we can even hit the drop down to see the full name. Now, if I hit fund, nothing's going to happen, right? Because my address is going to be sending 0. In order for me to send something, I have to add some value along with my transaction. So let's send, for example, 1 GUI, which is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, this much way. So before I hit fund here, if I copy this fake account, which is up here, and I put it in this address to amount funded, it's going to return 0. But now, if I add 1, 2, 3, 4, 5, 6, 7, 8, 9 in here, and we go ahead and hit fund now, we've now just called this fund function with a value of 1 GUI associated with it. So if I call this address to amount funded now with the same address, I can now see how much we've funded this smart contract. And we can even add more GUI. We'll add 11 GUI, for example. We'll call fund. And if we call this now, we can see that even more has been added. When we send our funds to a contract, this actually means that this contract, wherever this is deployed, now is the owner of this amount of Ether. So this is fantastic. We now have a way to fund our smart contracts. Now, here's the thing. In this smart contract, in this funding that we're doing, we want to create a minimum value for people to be able to fund our endeavors, which, whatever they may be. We want to set some minimum value here. And Ether is great, but for whatever reason, we want to work in USD, or maybe we want to work in some other token. So how are we going to get the conversion rate from that currency to a currency that we can use in this smart contract? Well, the first thing that we're going to need to do to set this value is we're going to need to know what the ETH to USD conversion rate is. Because if I want to accept Ethereum as the token, but I want it in its USD currency, well, then I'm going to need to know what that conversion rate is. So how are we going to get this data into our smart contract? Where are we going to get this data from? Now, remember how we talked about blockchains being deterministic systems and oracles being the bridge between blockchains and the real world? Well, this is exactly where oracles come in. When we're talking about these systems, these blockchains, they can't connect to real world events. They can't connect to external systems. They can't do external computation. They're intentionally these deterministic systems, these walled gardens. So in order for us to make this connection, we need a blockchain oracle. We need some type of network here. Now, just to get a little bit more technical for you, if we look at a blockchain can easily say 1 + 1 = 2, and every other node can easily verify this. However, a blockchain can't easily say, okay, let's all grab the same random number, because each node is going to get a different random number. They also can't say, hey, let's make an API call, because if one node calls the API at a different time, another node calls it, or specifically like an HTTP GET, there could potentially get very, very different results. And if another node tries to replay these transactions by calling these APIs again, maybe 10 years in the future, there's a good chance that that API is going to be depreciated. And they could be hacked, they could be malicious, etc., etc. The other reason that blockchains intentionally can't make API calls is because then they would be making assumptions about the real world. And layer ones typically don't want to have an opinion on any political or geopolitical issue, whereas an oracle network, on the other hand, can make those assumptions. The other main thing we need to talk about here is centralized oracles being main points of failures. If you or I say, hey, I'm just going to be the oracle, I'm going to be the one to put this data on chain, we now have this massive centralized point of failure. We've done all this work to make our decentralized computation decentralized and on-chain, but we ruin all the decentrality by having a single point of failure. Remember, one of the whole purposes of blockchain is so that not a single entity can flip a switch and restrict our freedom to interact. With a centralized oracle, a single entity can flip a switch and restrict our freedom to interact with each other. We also need to get data from many different decentralized sources or do any type of computation in a decentralized manner. This is where Chainlink really shines. Chainlink is a modular, decentralized Oracle infrastructure and Oracle network that allows us to get data and do external computation in a highly Sybil-resistant, decentralized manner. It can be as customizable as you want, as you can run with one node or many nodes, or do as many nodes as you like. Now, currently, one of the most popular features of Chainlink is their data feeds or their price feeds. We can even go check them out over at data.chain.link. We can see a number of different price feeds and the networks that are providing the prices for these specific pricing points. We can see here by looking at the UI, there's a whole number of decentralized different oracles returning data for different price feeds. This one, for example, is ETHUSD, and it's also exactly the price feed that we're looking for. Having a decentralized network bring this data on chain and have it as a reference point of definitive truth allows users to all collaborate and use this common good, and it will be cheaper, more secure, more efficient than anybody even running their own centralized oracle. So these price feeds are incredibly powerful. Additionally, they're being used by some of the top protocols in the DeFi system right now, like Synthetix, which at the time of recording is securing around $2 billion. SushiSwap for leveraging trades, Set Protocol, Commodity Money, Aave for understanding the price of an underlying collateral. Now, this is an example of an out-of-the-box decentralized solution that's already been packaged in a decentralized manner for you to consume and for you to use. This makes going to production 1,000 times easier than building everything yourself. However, if you want to make API calls and build your own decentralized network, you absolutely can with the Chainlink API calls. We're not going to go into that here because using the Chainlink price feeds, Chainlink VRF, Keeper Network, and all these other pre-boxed decentralized services are going to make going live and going mainnet a lot easier. You can always make a Chainlink HTTP GET call as well. We're not going to go over this though because putting this into production is a little bit trickier, and working with Chainlink VRF, if you ever want to try them out by themselves, you can always head over to docs.chain.link and head over to get the latest price feed. There's usually a remix button actually that we can click, and it will kick us out to a remix edition with all the code already ready to go for us. If we just hit this gist right here, this will include all of our code, which we'll go into in a second. But let's go ahead and compile it. We're going to deploy it to a real network here. This one looks like it's actually for Kovan, so we're going to go ahead and switch to Kovan. Looks like I don't have any Kovan Ethereum, so we're going to grab a Kovan faucet. We can usually find different faucets in the Chainlink documentation. Let's look up Kovan here. Aha, there is a Kovan faucet here. It looks like in order for us to get some Kovan Ethereum here, we have to log in with GitHub. Then we can add our address in here and get the Ethereum. In the interest of time, I'm going to skip ahead from me doing that. Great, it looks like I've got some Kovan testnet now. Being able to switch between testnets is going to make you a lot more effective as an engineer as well, because you're going to be able to understand how each network actually works. So now we've compiled this. Let's deploy this. Again, MetaMask is going to pop up. And let's go ahead and click the get the latest price, and we can see that this function does indeed return the latest price of Ethereum. Now you might be asking, why does this number look so big? Well, remember how we talked about Wei and Gwei and Ether? Well, the reason that those exist is because decimals don't work in Solidity. So we actually have to return a value that's multiplied by 10 to some number. So this value is actually 2,614 times 10 raised to the 8th. Now, the next question you might ask is, well, why did we work with this on a testnet? Why couldn't we do this on a local network? And the answer to this is because there is a network of nodes looking at this testnet and delivering data onto this testnet. When you spin up a local network or do a simulated VM, there are no nodes actually doing that. We'll learn later how to actually mock these interactions and mock a Chainlink node returning data onto our blockchain. But for now, let's head back over to the contract that we're working on so we can learn how to implement this in any contract that we ever want to. Another contract called, in this case called price feed, has a function called latest round data, which returns a lot of data. It returns a round ID, which defines how many times this price feed has been updated. It returns a price, which is the actual conversion rate between the two assets. It returns a started at, which defines when this was last updated. It returns a timestamp, and it returns an answered in round. Don't worry about answered in round for now. If you want to dive a little bit deeper into what these rounds mean and what answered in round means, you can definitely check out the Chainlink documentation and some of the FAQs to learn more. Now, how do we implement this data feed into our FundMe application? Well, the first thing we're actually going to need to do is we're going to need to import the Chainlink code. So we're going to do import at Chainlink/contracts /source /v0.6 /interfaces /aggregator v3 interface.sol. Now let's talk about what this is actually doing. Oops, looks like I spelled aggregator v3 interface wrong. All right, great. Now it's actually compiling. So let's talk about what imports actually do. As we know, an import will take whatever code you're importing and stick it at the top of your project. So when we import from @Chainlink/contracts, we're actually importing from the @Chainlink/contracts npm package. We can look up @Chainlink/contracts in npm, and we can see and read more about this repository. This links us back to the GitHub, which will tell us a little bit more about what's really going on. If we follow that import path that we got from the documentation, we'll end up on this file. In front of me now, we have what's called an interface. You can see these contracts don't start with the contract keyword, but they start with the interface keyword. They have the exact same Pragma Solidity at the top, but the main difference is that you can see that their functions aren't completed. They just have the function name and its return type. Now, just to be a little bit more explicit here, I'm actually going to go ahead and delete this import statement on the top and replace it with that interface code from GitHub, just to show you exactly what's going on. However, if you've already typed that @import syntax, feel free to leave it in there. And just remember that it's going to be the exact same as me copy pasting the interface code in. In our code here, Solidity doesn't natively understand how to interact with another contract. We have to tell Solidity what functions can be called on another contract. This is where interfaces are actually going to come in. Similar to structs, what we can do with interfaces is define a new type. So if we copy all this code from this section and place it at the top of our code here, above where we're declaring a contract, we can actually then interact with contracts that have these functions. If we go ahead and even compile this, we can see that this does indeed compile correctly. Remember how we said before, we talked a little bit about ABIs. Well, interfaces actually compile down to what's called the ABI, or the Application Binary Interface. The Application Binary Interface tells Solidity what functions can be called on another contract. We need Solidity to know what functions it can use and what functions it can call other contracts with. And if that was a little bit confusing, just know anytime you're going to interact with another contract in Solidity or smart contract programming in general, you're going to need that contract's ABI. We'll go into what these ABIs look like a little bit later. Anyways, to simplify it, interface compiles down to an ABI. We always need an ABI to interact with a contract. So how do we actually work with this contract here? To interact with an interface contract, it's going to work the exact same way as interacting with a struct or a variable. Let's define a new function called getVersion, and we're going to call this version function on this other contract. So we'll start out doing function getVersion public. Remember, it needs to be a view since we're just going to be reading this state, and even in the interface, it even defines it as a view returns. So we'll even grab this whole bit right here. View returns uint256. Now, the exact same way we define variables and structs, we define working with other contracts and interfaces. So the first thing is we name the type, which in this case is aggregator v3 interface. Then we'd name the visibility. But since again, we're inside of this contract, we're going to skip it. Then let's give it a name. We'll call it price feed, since this aggregator v3 interface is going to be giving us a price feed. Then we can do equals, and this is where we're going to initialize the contract. So how do we actually choose where to interact with this contract? Well, we just type aggregator v3 interface, and then we put in here the address of where this contract is located. In order to find where this ETHUSD price feed contract is located on the Rinkeby chain, we can look at the Ethereum price feeds Chainlink documentation. It has a ton of different price feeds and even more not price-related data. Let's scroll down to Rinkeby because, again, on each different chain, the contract address that has all this price feed information is going to be different. Let's scroll down and find ETHUSD, which is right here. And we'll copy it and we'll paste it into here. Now, what is this line saying? It's saying that we have a contract that has these functions defined in the interface located at this address. If that's true, then we should be able to call pricefeed dot version. And we should be able to return it. Whoops, looks like we forgot to add those here. And we need a semicolon here. I hit Control S or Command S, compiles. It looks like we're compiling successfully. And we do need to deploy this on a testnet. Remember, this address here is located on an actual testnet. It's located on an actual network. It's not going to be located on our simulated chain here. So we do need to deploy this to injected Web3. We do need to deploy our contract to Rinkeby because the Rinkeby chain has this address. We'll learn later on how we actually can work with a simulated chain and work with these price feeds, but that's much later in this course. So let's go ahead and save. We'll deploy, make sure we're on injected Web3. Now we can go ahead and hit deploy. MetaMask is going to pop up per usual. Confirm. We're going to get a transaction link to Etherscan showing us our contract. And once it actually is confirmed, we can see we have our contract right here. Now we have our familiar functions with one additional function. We have our fund button, which is red because it's payable. We have our address to amount funded mapping, which is blue because it's a view. And we also have this get version button that's also blue. If we go ahead and click it, we can see that the version of our aggregator v3 interface is version 3. This is the third version of the aggregator interfaces, hence the name, aggregator v3 interface. So we just made a contract call to another contract from our contract using an interface. This is why interfaces are so powerful, because they're a minimalistic view into another contract. So this is great. We have a get version function, but this still isn't the function that we want. We want to call the get price function, which if we look at our interface, we can see there's a latest round data function that returns an answer. This is the function that we're going to want to call on this contract. So let's go ahead and make a function that calls that instead. So we're going to do function get price public view returns uint 256. This latest round data function though returns 5 variables. So how do we actually work with that? Well, let's find out. To work with this contract, we're going to do the exact same thing. We're going to do aggregator v3 interface because this is the type of the contract. Price feed equals aggregator v3 interface. We'll do this same address in here because this is the ETHUSD address. Then we'll do price feed dot latest round data. Now, since this is going to return 5 different values, we can actually have our contract also return these 5 different values. We can copy paste like this and literally do this, these 5 values equal price feed dot latest round data. And you can see that even compiles correctly. Let's adjust the formatting a little bit here so it looks a little bit nicer. A tuple is a list of objects of potentially different types. This is the syntax for getting a tuple. We can define several variables inside one of these tuples. Although our compiler is going to give us some warnings. It's saying unused local variable because we're not actually using these for anything. We'll come back to this. Now we can go ahead and do return, and we can pick one of these variables that we want to return. Answer is going to be the price. So we're going to do return answer. But we're going to run into an error. Return type argument int256 is not implicitly convertible to expected type. Answer is an int256, and we want to return a uint256. So how do we rectify this? We can fix this by using what's called typecasting. If we just return answer, we're going to be returning the wrong type. However, integers and Solidity are really easy to cast into each other. So we can just do uint256 and wrap it around this answer, and then compile and save that instead. As you can see, now our compiler is happy because we've changed this answer into a uint256. Awesome. So now this get price should return the latest price of Ethereum in terms of USD. Let's go ahead and deploy this new contract with this new function. So same thing, we're going to come to our deploy section, hit the deploy button. Remember, we got to go to the fundme.sol. Let's deploy it. Confirm with MetaMask here. And let's scroll down to our newly deployed contract. As you can see, we have our get version function, which still works exactly the same, but we have a new function too, called get price. And this should return a uint256 answer. Let's go ahead and click it. Amazing! We've actually returned an answer. Now, again, if you're a little confused on why this number looks so big, you have to remember that this actually has 8 decimals. We could call this decimals function on the contract to learn that. 1, 2, 3, 4, 5, 6, 7, 8. And we know that the current price of Ethereum in terms of USD is 2,482. Awesome. So now that we have the price, we can actually get the conversion rate. But let's clean up this function a little bit before we go on up there. As you can see, one thing that the compiler is complaining about is we have a lot of unused local variables. But latest round data returns 5 different variables. So how do we actually return the 5 variables, but make our compiler happy with us? Well, we can actually just return blanks for each one of these sections with commas in between each other to say, hey, there is a variable here, but we're not going to use it. This will also make our code look a lot cleaner because now this function's a lot smaller. We say, something's here, we're ignoring it. int256 answer we're going to use, something's here, ignore it, something here, ignore it, and ignore this too. And we can even test this out by compiling it, deploying it, checking on RinkB, scrolling down, hitting this, and hitting get price. And you can see, indeed, it's the exact same as before. Awesome. So now we're all done cleaning things up, right? Not quite yet. See, the other thing that's really annoying here, we have this massive chunk of code at the top that is probably a little redundant. There's a good chance that a lot of our contracts are going to want to use this aggregator v3 interface. So let's just go ahead and add that @chainlink/contract syntax backend because it's going to look a lot cleaner here. And do @chainlink/contracts. If you ever get a little bit confused with what you should be importing to work with their contracts, we can see right in the documentation at the top, this @syntax is what this is going to use. Now you can also go ahead and browse that npm package of @chainlink/contracts to see what other applications are in there and what other files are in there, or you can just peruse around the GitHub. Now, the third way we can actually do imports is we can import from contracts that are in the same file system as our contracts. Well, awesome. Our contract is starting to look more and more put together. Now, one other thing that I usually like to do with these is I usually like to put everything into the Gwei Wei standard. So as we saw, this get price had 8 decimal places. However, the smallest unit of measure, aka Wei, if we look at it, has 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So typically in these, I like to try to make everything have 18 decimals as well. You don't have to do this and it'll save some gas if you don't, but I usually like to multiply everything so that everything has 18 decimal places. So since I know this has 8, I can just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now this will return the price with 18 decimal places instead of 10. Now we have the price of Ethereum in US dollar, which is fantastic. So we could set the price of our funding function to anything that we want here. For example, let's say $50. We could convert whatever value that they send us to its US dollar equivalent and see if it's greater than or less than $50. All we have to do is make a new function that converts that value that they send to its US dollar equivalent. So we could do function get conversion rate, and it'll take a UINT 256 F amount. Let's get this out of the way for the rest of this. It'll be a public view function, since again, we're not actually going to have it make any state change. We'll do returns UINT 256, and then in this function, we can do UINT 256 F price equals get price, and we can call this get price function up here. Now we have the price in here. What we want to do is we want to convert whatever value that they send as F amount. Let's say they send 1 gwei, or again, that's going to be this much wei. How do we convert this to FUSD? Well, we can now do UINT 256 F amount in USD equals this F price times the F amount that they sent. This is actually going to result in a much bigger number than we're looking for. And then of course, we're going to return it. Let's test this out and see why we have to do one more thing here. So let's again, fundme, we'll deploy rinkb, and we'll scroll down, and we have this new function called get conversion rate. Let's grab this 1 gwei and put it in here. Whoa, this seems like it's a really big number. We're saying that 1 gwei is equal to 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This many dollars. Now, I don't know about you, but I don't think the price of even 1 Ethereum is that many dollars. Maybe in the distant future, but definitely not right now. The reason that it's off is we have to then actually divide by this number. The reason that we have to do this is because both F price and F amount have an additional 10 raised to the 18th tacked onto them. So now we have to divide it out in order to get the right number. So we're going to compile, deploy, confirm. We can scroll down, and now let's try this 1 gwei. We'll get the conversion right here, and we can see we get a number that makes a little bit more sense. Now remember, this has 18 decimals as well. So the real number is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know that this number is actually accurate because we can go ahead and pull up a calculator, pop that into here, and we know that this is 1 gwei in US dollar. If we get the conversion rate, we're saying that this many gwei equals 1 ETH. So we can check it back by multiplying this number by that, and we see that we do actually get the price of 1 Ethereum in US dollar. So our math here checks out. Awesome. Now, since we're on the topic of math, I do want to talk briefly about some of the pitfalls of Solidity, especially when it comes to math. Prior to Solidity 0.8, if you added to the maximum size a UINT number could be, it would actually wrap around to the lowest number that it would be. And in fact, you can even demo this with a contract here. Now, you don't have to follow along with this contract, but just watch to see the example. We're going to call this overflow.sol. Now in here, we're going to add all kind of the normal stuff, contract overflow, and we're going to add a function called overflow. We'll make a public view, and we'll have it return a UINT 8. I'll show you why in just a minute. A UINT 256 is a really, really big number, and it's hard to kind of imagine going over the maximum cap of a UINT 256. But a UINT 8 is a lot smaller, with the maximum number actually being 255. So if we create a UINT 8 and we call it big equals 255, and then we just do return big, what do we think we're going to get here? For this, we can go ahead and use JavaScript VM because we're not interacting with any other contracts. Let's deploy this. And we'll see in our contract, if we call overflow now, we're just going to get 255. However, what happens if we add 1 to this number or try to add 1 to this number? If we do it just like this, Solidity actually knows that there's an issue here and says, hey, try not to do this. But if we typecast this as a uint 8, Solidity gets a little bit more confused and goes ahead and lets us do this. Now, what do we think big is going to be? It should be 256, right? But big is a uint 8, and this is the maximum size that it could be. So what happens when we deploy this? We look down. We actually get 0. What happens if we do 100 and we deploy that? We actually get 99. And this is because integers can actually wrap around once you reach their maximum cap. They basically reset. This is something we need to watch out for when working with Solidity. If we're doing multiplication on really big numbers, we can accidentally pass this cap. Luckily, as of version 0.8 of Solidity, it actually checks for overflow, and it defaults to check for overflow to increase readability of code, even if it comes a slight increase of gas costs. You can use this unchecked if you want to have it keep that wrapping functionality. So just be aware, if you're using a lower version than 0.8, you're going to have to do something to make up for this. And we could write a whole bunch of code here basically to check all of our math, or we could just import something called SafeMath from another package. Similar to how we imported Chainlink, we can go ahead and import a package called SafeMath from a tool called OpenZeppelin. Now, OpenZeppelin is an open source tool that allows us to use a lot of already pre-built contracts. We can go ahead to their documentation and go to their utilities and see SafeMath. And they even have a little sticker here saying, SafeMath is no longer needed, started with Solidity 0.8. SafeMath is a tool and a way for us to avoid some of these problems with doing math in Solidity. Now, I'm not going to spend too much time on the contracts that actually fix this, but we can actually import right from the Chainlink directory as well a Solidity file called SafeMath Chainlink. And what we can do is right after our contract, we can do using SafeMath Chainlink for uint 256. And what this will do is it'll use SafeMath Chainlink for all of our uint 256. And SafeMath Chainlink doesn't allow for that overflow to occur. Libraries are really similar to contracts, except that they're isolated code that can be run in a reusable context. In this case, we're attaching the SafeMath Chainlink library to uint 256 so that these overflows are automatically checked for. Just keep in mind, if you're using anything less than 0.8, you're going to want to use some type of SafeMath just to check for your overflows. Now, this is for those of you who are familiar with SafeMath and integer overflows and underflows. We are not going to be calling the functions that SafeMath provides us, like div, add, mul, all those functions. Simply because in 0.8 moving forward, we no longer have to use those, and we can just use our regular operators like plus and minus. So this is great. Our contract is coming along really well. We now have a way to get the conversion rate of whatever F is sent and turn it into US dollar. Now we can set a threshold in terms of US dollar. But how do we guarantee that whatever amount that the users send when they call fund is going to be at least $50? Well, first we might want to set a minimum value. So we can do uint 256 minimum USD equals, let's say, $50. And again, since we're using everything in GUI terms, we want to then multiply this by 10 raised to the 18th. And just wanted to take a pause for a second because this line is actually wrong. This should be raised to the 18th. So this line should really look like this, where it has the double star. So apologies, the rest of this has that single star, but it should be the double star here. If you do have the single star though, the rest of the contract will still work fine. So this will be the minimum value. It'll be $50 times 10 raised to the 18th so that everything has 18 decimals. Now that we have a minimum amount, how do we actually make sure that this minimum amount is met in the value that they send us? Well, if you're familiar with if statements, we could do something like if message.value is less than minimum USD, then revert. Or we could do something a lot easier and better practice and much cleaner. We could do what's called a require statement. When a function call reaches a require statement, it'll check the truthiness of whatever require you've asked. So in our case, the converted rate of message.value needs to be greater than or equal to our minimum USD. This line says that if the conversion rate of message.value to USD, if they didn't send us enough Ether, then we are going to stop executing. We're going to kick it out. We're going to say, hey, this doesn't count, and we're going to do what's called a revert. We're going to revert the transaction. This means that the user is going to get their money back as well as any unspent gas, and this is highly recommended. We can also then additionally add a revert error message, something like, you need to spend more ETH. So now let's try this out. As we saw, 1 GUI is going to be way less than $50. So if we send 1 GUI along with this fund contract call, it should kick out and say, you need to spend more ETH. So let's actually try this. Let's go to the deploy tab. We'll get rid of our overflow. We use injected Web3 because, again, we are working with the Chainlink aggregator contracts that are on chain. We're going to move to fund me, and we're going to hit deploy. MetaMask is going to pop up, and we're going to hit confirm. Now, if I try to hit fund, let's see what happens. We're getting a gas estimation failed. It says gas estimation error failed with the following message. Execution reverted. You need to spend more ETH. So the contract isn't even letting us make the transaction. We can go ahead and try to send the transaction, but here's what's going to happen. On Etherscan, once this goes through, you can see that once this transaction finished, we got this status, fail with error. You need to spend more ETH. We don't want to force these transactions to go through. If we look in our MetaMask, we can even see this failed bit here. So whenever you see these gas estimation failed errors, usually that means something reverted or you didn't do something that was required. However, if we go to value here and we spend a lot more, let's say 0.1 Ether, which if we take out our calculator, 2500 times 0.1 is going to be $250. This should easily be well and beyond past our $50 threshold. So let's add 0.1 Ether. And remember, we got 0.1 by adding it in the converter and grabbing the Wei. Again, the Wei is the smallest denomination. Now, if we change this to Wei and hit fund, this should go through. We go and hit fund now. You'll see MetaMask pops up because MetaMask goes, oh yeah, this transaction isn't going to revert. And that's what we want. So we can go ahead and hit confirm. And now we'll finally have sent some funding to our contract. And now that this is confirmed, we can go ahead and grab our address here, pop it into our address to amount, and we can see that indeed our funding has gone through. Now we can be part of this crowdsourcing application with our minimum value, which is fantastic. Awesome. Great job. Awesome. So now we can fund this contract with a certain minimum USD value. In this case, it's going to be $50. Now, you'll notice though that right now we don't do anything with this money. So we're going to fund this contract. However, that's it. And we don't have a function in here to actually withdraw the money. So there's no way that even though we just sent this contract some money, there's no way for us to get it back. So how do we fix this? Well, we can add a withdraw function in here. So let's go ahead and add that. Function withdraw. And this is also going to be a payable function because we're going to be transferring ETH. We'll make this public. And we can do message.sender.transfer. Transfer is a function that we can call on any address to send ETH from one address to another. This transfer function sends some amount of Ethereum to whoever it's being called on. In this case, we're transferring Ethereum to message.sender. So all we need to do now is define how much we want to send. Well, we're going to send all the money that's been funded. So to get all the money that's been funded in this contract, we can do address this.balance. Now, there's a couple of special things going on with this line. First, we're saying address of this. This is a keyword in Solidity. Whenever you refer to this, you're talking about the contract that you're currently in. And when we add address of this, we're saying we want the address of the contract that we're currently in. Whenever you call an address and then the balance attribute, you can see the balance in Ether of a contract. So with this line, we're saying whoever called the withdraw function, because whoever calls the function is going to be the message.sender, transfer them all of our money. So let's go ahead and try this. Let's deploy FundMe. And now let's fund this with a lot of Ether so that we can see it. We'll fund it with one whole Ether so that we can see it go into the contract and get pulled out of the contract. We'll hit the fund button and you'll see we're sending one whole Ether into this contract. Now, if we look at our balance, it's gone down from 17 to 16. Or if you're still at 18, it went down from 18. So let's try to get it back. If we call this withdraw function now, confirm, once this transaction goes through, we should get all of our Ether back. Let's look at our MetaMask and boom, indeed, we have got all of our ETH back. However, looking at this contract, we can see that, well, maybe we don't want anybody to be able to withdraw all the funds in this contract. That seems like it might be a really bad idea. Maybe we only want the funding admin to be able to withdraw funds. So how do we set this up in a way that only the contract owner can actually withdraw funds? Well, we learned before that the require function can actually stop contracts from executing unless some certain parameters are met. We can do the same thing here with require message.sender equals the owner. But we don't have an owner to this contract yet. So how do we get an owner to this contract the instant that we deploy it? Well, we could have a function called create owner. But what happens if somebody calls this function right after we deploy it? Well, then we wouldn't be the owner anymore. So we actually need a function to get called the instant we deploy this smart contract. And that's actually exactly what the constructor does. So typically at the top of your smart contracts, you'll see a constructor. And this is a function that gets called the instant your contract gets deployed. We don't even need to do add function here. We can literally just call it constructor because it's what constructs the smart contract. So we'll make constructor public, and whatever we add in here will be immediately executed whenever we deploy this contract. So one thing that we could do is we could have an owner be set the instant we deploy the smart contract. So in the top, we could add address, owner. And in our constructor, we could say owner equals message.sender. Because the sender of this message is going to be us. It's going to be whoever deploys this smart contract. We can even test this out in the JavaScript VM to be a little bit quicker because we're not actually going to be calling the fund or the get price function for now. Oops, let's also make this public so that we can interact and see this owner variable. So now if we go to FundMe, we deploy this in the JavaScript VM, we should be able to see who the owner of this contract is. And it should be our address because this constructor function should have been immediately called the instant that we deployed the smart contract. Awesome, we can see the owner of this smart contract is indeed our wallet. Because remember, when we're working with the JavaScript VM, our wallet is these fake wallets that they kind of give us. We can even try this with an injected Web3 with deploying this. And the owner should be this OX757, etc. address. Let's go ahead and look at FundMe, see the owner, and we do indeed see the owner is us. Okay, great. Now we have an owner. We can go down to our withdraw function and use that same require. So we can call require message.sender equals owner. Equals is the way that Solidity understands true false. We're saying that message.sender has to equal owner. Now let's go ahead and try this. And we'll try it with the JavaScript VM again for speed reasons. Let's deploy this FundMe. And if we go down here, we can try to call the withdraw function. And it looks like it is successful because currently this is the address that deployed the contract and it's also the address that is calling withdraw. However, If we switch to a different account and call withdraw, you'll see that Remix actually freaks out down here. It says, uh-oh, something wrong happened. And this is essentially the require statement kicking out. If you want to try it with injected Web3 as well, we can absolutely do that too. And remember, the way to switch accounts in MetaMask is to either create account right here or just switch like this, and then we'll connect with account 2. So if I try to withdraw from this second account that didn't call the contract, and I hit withdraw now, it's going to give us gas estimation failed because the require statement is going to kick out. But again, if we switch back to account 1 and we call withdraw, MetaMask is going to pop up and it's going to allow us to withdraw. Now, obviously, there's nothing in this contract right now, so we're going to withdraw nothing, but we can still call it. It's going to do message.transfer 0. So this is great. We can now require this withdraw function is only callable by the owner. Now, what if we have a ton of contracts that want to use something like this? They require the message.sender to be some owner, or maybe it's more complicated than this. Is there an easier way to wrap our functions in some require or some other executable? Well, this is where modifiers come in. We can use a modifier to write in the definition of our function, add some parameter that allows it to only be called by our admin contract. Modifiers are used to change the behavior of functions in a declarative way. Let's create our first modifier. We'll call it modifier, which is a keyword, only owner, and we'll add this require statement in here. Require message.sender equals owner. Then after this, we just add an underscore and a semicolon. What a modifier is going to do is it's going to say, hey, before you run this function, do this require statement first, and then wherever your underscore is in the modifier, run the rest of the code. So we could also do a modifier where the underscore is up here, and then this is afterwards, but we want to run the require first. So now what we can do is we can make this function withdraw payable only owner public. And what's going to happen is before we do this transfer, we're actually going to check this modifier. We're actually going to run this require message.sender equals owner. And then, again, where this underscore is, that's where we'll add the rest of the function. So again, for speed reasons, and since we're not actually going to be interacting with the Chainlink data contract, we can go to JavaScript VM, switch to fundme, deploy, and we can call withdraw. Obviously, we can call withdraw from our account, but if we switch accounts and try to call withdraw, we're going to get an error, which is perfect, because that means our modifier is working correctly. Awesome. Now we have a fantastically succinct fundme contract here. The only thing that we're really missing is that when we withdraw from this contract, we're actually not updating our balances of people who funded this. So even after we withdraw, this is always going to be the same. So we need to go through all the funders in this mapping and reset their balances to 0. But how do we actually do that? We can't actually loop through all the keys in a mapping. When a mapping is initialized, every single key is essentially initialized. Now, we obviously can't go through every single possible key on the planet. However, what we can do is create another data structure, an array, something we're already familiar with. So let's go ahead and create a new funders array. That way we can loop through them and reset everyone's balance to 0. We'll do an address array because it's going to be an array of all the funders' addresses. We'll make it public and we'll call it funders. Now, when somebody funds a contract, what we're going to do is we're going to do funders. Now, whenever a funder funds this contract, we can go ahead and push them onto our funders array. So we can do funders.push message.sender. Now, if somebody funds multiple times, the funders array is going to be a little bit redundant, but we're going to ignore that for now. Now that we have an array of funders, when we withdraw everything, we're going to want to reset this to 0. When we withdraw everything, we want to reset everyone's balance in that mapping to 0. So we're going to do what's called a for loop. A for loop is a way to loop through a range of numbers to do something. So we're going to say for uint256 funder index equals 0, because we want to start with the 0th index. We're going to give it a max size to go to. We're going to say the funder index has to be less than funders.length. .length is how we get the length of our array. And then we're going to say funders index plus plus. This means that we have an index variable called funder index, and it's going to start from 0. This loop is going to finish whenever funder index is greater than the length of the funders. Every time we finish a loop, we're going to add 1 to the funder index. That's what that funder index plus plus does. It adds 1 to the funder index. And every time whatever code is in this for loop executes, we're going to restart at the top. And all we're going to do in here is we're going to grab the address of the funder from our funders array. Funders. So the funder at the index in our funders array, we're going to use this as the key in our mapping. So we're going to take address to amount funded of funder, and we're going to set it equal to 0. So now our mapping is going to be all updated to people having 0 funded in there. We do have to do one more thing as well. We have to reset our funder array as well. Now there's a couple ways to do this, but a really easy way is just to set funders equal to a new array. So we can do funders equals a new blank address array. So all right, it looks like we've got everything in here we need. Right away when we deploy this, we are set as the owner. We can allow anybody to fund whatever public good that we're doing. And they have to fund it with the minimum USD value that we actually set. Whenever they fund, we'll keep track of how much they're funding and who's been funding us. We can get the price of the Ethereum that they send in the terms of USD. And we can convert it to check to see if they're sending us the right amount. We have our only owner modifier so that we're the only ones who can withdraw from the contract. And when we do withdraw everything from the contract, we reset all of the funders who have currently participated in our crowdsourcing application. Awesome. Let's see if everything works end to end. So we're going to go to FundMe. We're going to deploy it. We're going to confirm from MetaMask. And remember, if you're ever confused about what's going on or something weird is happening in your transactions or your deployments, you can always go into Etherscan and read more about your transaction and what's going on. Now that our transaction has been deployed, let's go ahead and just take inventory as what's going on. We have our owner, which is our address right here. We have the aggregator v3 interface version, which is version 3, which we can kind of ignore. We have the price of Ethereum in terms of USD with 18 decimals instead of 8. We have a function that allows us to get the conversion rate of any Ethereum amount to its US dollar equivalent. We have an array of funders, which right now starts out as empty. We have a mapping of addresses, which also right now starts out as empty. Let's go ahead and try to fund this contract. We'll use Wei, just so that we're always on the same page, and we'll fund it with 0.1 Wei. Remember, everything has 18 decimal places. So if we want to do 0.1, we just do 17. So we can do 1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that'll be 0.1 Ethereum. Now we can go ahead and hit fund, and we're going to send 0.1 ETH to this contract. Great. So if we look at the 0th index of funders, we can see that indeed we have funded this contract. Let's even have our second account fund this contract. So all we got to do is switch to this contract in MetaMask. We can go ahead and put 0.1 ETH back in here for value and hit fund. Now, as you can see, we're deploying this from account 2. Let's go ahead and hit confirm. Funder at index 0 is going to be our admin, and the funder at index 1 is going to be our second account. And if we go ahead and we add this funder in here, we can see we've indeed sent 0.1 Ether with this account. If we go back to our account 1 and put this in here, we can see that that address also has 0.1 Ether. Fantastic. So let's try to be malicious. Let's try to have account number 2 actually withdraw all the funds in here. Let's hit this withdraw function. Uh-oh, the transaction has failed. We're relentlessly malicious. We want to send this transaction regardless. So even though I'm not the admin of this contract, I've gone ahead and still tried to send this withdraw. So what happens now? We can see that Remix is saying, hey, something went wrong. And again, if we look at Etherscan, we can see that there was a fail here. Since in our modifier, we didn't give a reason here, nothing shows up. But we could have always put a reason in there and something would show up. So, all right, let's go ahead back to the actual admin. And now let's try to withdraw everything. So if we hit withdraw now, we can go ahead and confirm. What should happen is everything in here should be back to 0, and this array should be back to 0 as well. And if we watch our address, we can see it literally just went from 0.4 to 0.6 because it got 0.1 from the original funding that this account put in and the 0.1 that our second account put in. So now if we look at funder 0, we can see it actually errored because it is now a brand new array and there is nothing at index 0. If we try to see how much this address now is funded, it's back down to 0. Awesome, you've now learned how to deploy a relatively simple yet effective crowdsourcing application where users can fund and an admin can withdraw those funds to go spend them on things. Now we've been working with Remix so far to start our smart contract and our Solidity development journey. Remix is an incredibly powerful what's known as a web IDE, or an integrated development environment. And in my opinion, Remix should always be the starting ground for anybody looking to start their smart contract journey, because it is a wonderfully friendly way to really show what's going on behind the scenes. And it's really easy to see everything we're doing with Ethereum, with Chainlink, and with our smart contracts. Now, it does have some limitations though. It's really hard to integrate other parts of different projects. It has some limited support for testing or custom deployments. It's a little tricky to save files locally. You need an internet connection to actually interact with it, and it doesn't have Python. So in order for us to deploy, test, and automate everything about our smart contract development cycle, we want to connect our Solidity and our smart contracts with a more traditional programming language like Python. This way we can customize our entire development environment in any way that we like. We're first going to teach you all how to work with what's known as web3.py, which is an incredibly powerful Python package for doing everything that we want to do with smart contracts. Then once we learn some of the basics of web3.py, then we'll move on to Brownie, which is a smart contract development framework built on top of web3.py, which makes our lives even easier. However, it's still really important to learn web3.py first because this will teach you what's going on behind the scenes of Brownie. Now, for the rest of this course, I'm going to be working with Visual Studio Code, which is an incredibly powerful text editor that will give us a lot of formatting and a lot of really nice tools to work with deploying and interacting with our smart contracts. If you've already got VS Code and Python and your entire coding setup set up the way that you like it, feel free to use the timestamps in the description to skip ahead to the next section. You'll often hear people referring to this as VS Code or Visual Studio Code. But just to point out, this is not what you're looking for right in front of you here. Visual Studio is a different application. Make sure you're on Visual Studio Code. If you want to be a total hardo and just work with Vim or Emacs or whatever else you want to do, you absolutely can, but I'm going to go through setting up Visual Studio Code the way that I like it. And if you guys want to follow along, I highly recommend it because it's going to make your life a lot easier. There's a link to download Visual Studio Code in the GitHub repository. Basically, all you have to do is come to the site right here and you can hit this big download button. It should recognize what operating system that you're on, be it Windows, be it Mac, or some other operating system. And if it doesn't, you can go ahead and hit this little drop down and pick one there. So let's go ahead and download Visual Studio Code and open it up. Awesome. Once you've downloaded Visual Studio Code, this is approximately what you should be seeing. There's a fantastic getting started section here where if you're brand new to VS Code and you want to learn a little bit more quickly, you absolutely can. And we have some links as well in our GitHub repository, giving you a crash course in VS Code if you want to learn more. Let's set this up though, so it's going to be really friendly for us to be doing our smart contract development here. So first, we want to go to this extensions tab. It looks like these little blocks thing right here. And first, we're going to look up Python. And you want to install this Python extension right here. This is going to make our lives a lot easier for interacting with Python and doing a lot of things with Python. Then you're going to want to go ahead and download this and install this Solidity extension. This is going to make formatting our Solidity a lot easier. Now we want to download Python if you haven't already. So go ahead to python.org. Let's go to downloads, and it should recognize what operating system that you're on. And you can just go ahead and hit the download button and then follow the steps to download this. I've already got it downloaded, so I'm not going to walk through this. Okay, great. Now that we have Python installed, one of the other amazing things about VS Code is you can actually open a terminal up inside of Visual Studio Code. The way you can open your own terminal, if this is your VS Code, you can go over on this top bar to Terminal and select New Terminal. And you'll see something that looks like this. It might be a bash, it might be a ZCH, it might be a PowerShell. There's a lot of different types of terminals that you'll be able to see by looking right here. We can now test to see if Python is installed correctly. If we type in Python space -- version, we should get something that looks like this. The exact version of Python doesn't really matter here, but ideally you're at least on Python 3.8. If Python -- version doesn't work, you could also try Python 3 -- version. Now, if neither one of those works, we actually have a number of troubleshooting tips in the GitHub repository for this course. And oftentimes, a quick Google search on whatever error that you have, you'll get a link which will lead you to the answer. But if that Google search doesn't lead you to the answer, then just go ahead and drop an issue or a conversation associated with your issue on the GitHub repo associated with this course. In particular, there are a couple of common errors that I've definitely seen a number of times. So if you see an issue on your instance that matches something on the screen here, definitely 100% be sure to check out those troubleshooting tips. Sometimes just installing some of these applications is really the hardest part of doing the entire coding journey here. So please make sure you have Python and VS Code installed correctly before moving on. And don't be discouraged if this doesn't work exactly the way that it should right away. Now, if you're on a Mac, you can actually hit Control backtick and it will toggle back and forth between having the terminal open and closing it. I find this really helpful and I use it all the time instead of hitting the buttons. A key tip for productivity is going to be using keyboard shortcuts instead of clicking around all the time. You'll be much faster. Okay, great. We have Python installed. We have Python and Solidity extensions of Visual Studio Code installed. Let's start working on a new project. So in our terminal, we can create some folder. I've already created a demos folder here. You can create one as well if you'd like by doing mkdir demos. Since I've already done it, the file already exists, and then cd into demos. You can type clear, or if you're on a Mac, Command K to clear the terminal. Now, here's what we're going to be doing. We're going to be working with Simple Storage again, the exact same contracts, but instead we're going to be using web3.py. So we're going to make a new directory inside of our demos folder / directory called web3.py simple storage, and we're going to cd into this new folder right here. Now, again, all the completed code is going to be in our GitHub, and there's going to be a link to everything that we do in this folder in this GitHub. So you can always refer to that if you get lost. And the next thing that we want to do is we want to have our Visual Studio Code know that we're in this folder. So we can go ahead and click this files icon and hit open folder. And I'm just going to go to this web3.py simple storage and hit open. And another VS Code will actually pop up. We can see on the left-hand side here, we have a folder. This will show all the different files and folders in our web3.py simple storage directory. Let's go ahead and create a file .sol. We can right-click on this area and select New File and do simple storage.sol. And then we can go back to our simple storage.sol in Remix, copy everything, and then paste it into here. If you don't have it up, remember you can always refer back to the GitHub repository, which will have it in there for you. Awesome. Now we have our Solidity in its own file called simplestorage.sol. You'll notice that some of the words are actually highlighted different colors. This is known as syntax highlighting, and it's due to the fact that we added the Solidity extension in. It makes reading this code a lot easier. Now that this file is in here, we'll see that we have this little dot here. Whenever you see this little dot, this means that your VS Code file isn't saved. So we want to always save it. Otherwise, when we compile or we go to run a script, things might not work correctly. So we can save it by going up to File and then selecting Save. Or again, you're going to want to learn how to do the keyboard shortcuts because you're going to want to hit Save often. For Mac, it's Command S. And for Windows, it's Control S. Now, the other thing that you'll see is you get this red line here. This is VS Code's way of telling us it thinks that there's an error at this position. So this is really just the extension being a little bit confused here. And we can safely ignore this. And normally when I'm coding, I do just ignore it. We're often going to be flipping back and forth between compiler versions, so oftentimes this isn't really a helpful warning here. But if it is really bothersome, you could right click it and do something like Solidity change global compiler version, or we can go to Code, Preferences, Settings. Let's close this so we can see some more things in here. We'll look up Solidity and we'll come to this Solidity extension config. What we can do then is scroll down and we can see Solidity compile using remote version. This will allow us to choose what version we want to compile with. If we do 0.6.0 and hit save and go back to simple storage, you'll see the red line is now gone. While we have this up, another really helpful piece that we can do here is we can add what's called a formatter. So if we scroll down to Solidity formatter, you'll see that this enables/disables the Solidity formatter. We can go from none to prettier. Then we'll also look up format on save, and we want to make sure we have this editor format on save checkmarked. What we can do then is we can come over to simplestorage.sol, and maybe I've got some bad formatting in here. We'll move over favorite number, string name, and put a whole bunch of new spaces in here or something. Now, if I hit save, it automatically reformats our file to look a lot nicer. So to recap, we want to turn on format on save. And if you get issues with a red line under Pragma Solidity, you can just change the compiler version in your settings here. Now, while we're in here, we're also going to go ahead and set up our Python formatting as well. So the first thing that we're going to do is we're going to install the black Python formatter. So we're going to open up our terminal here. And whenever you install Python, it comes pre-installed with this package called pip. To check to see if you have pip installed correctly, run pip -- version. Now we can install the black formatter by running pip install black. I already have it installed, so it's going to be pretty quick for me. Then we'll come to our settings and we'll look up Python formatting, and we'll scroll down to Python formatting provider. You might have AutoPep8 or none in here. You're going to want to change it to black. This way, whenever we save our Python files now, they will also get automatically formatted to be very readable and really nice. And just to note, for my demos in Solidity, I don't always have format on save for Solidity. I do have format on save for my Python, but I'm still going to highly recommend you have format on save for both your Python and for your Solidity anyways. So how are we going to actually deploy this? Well, this is where our Python is going to come into play. Let's go ahead and create a new file on the left here, and we'll call it deploy.py. Now let's go into this deploy.py file, and let's start actually figuring out how we can deploy this in Python. And this is the part of the course where we start using Python here. If you're unfamiliar with Python or a little bit weaker on Python, there is a fantastic free code camp course that goes through all the basics of Python. If you want to learn more, I definitely recommend checking it out. However, we are going to walk you through all the scripts that we write anyways, so don't be afraid to just jump in and follow along with what we're doing here, even if you have no experience. So the first thing that we're going to want to actually do is read this simple storage Solidity file. We need to get this into this deploy script so that our Python file knows what it's going to deploy. So how do we do this? Well, we're going to type with open quote / simplestorage.sol, R as file, simple storage file equals file.read. Now, what is this actually doing? Well, it's saying that we're going to execute some code inside this indented area after the colon. And then once this code is finished, we're actually going to close this file. Because right now we're opening it, we're going to close it once it's done. The file that we're going to open is going to be this simplestorage.sol, which is located right here in this same directory that we're in. We're going to only read from it, and we're going to call it file. And then we're going to read all the contents of this file and place it in a variable simple storage file. So then we can go ahead and write a print statement, print simple storage file. And if you hit save here, you'll see that it automatically gets formatted, which is really nice. If you want to run black yourself, you can just type black dot, and it'll automatically format all the Python files in your folder here. You'll know that you're doing it right if you add a whole bunch of new lines and then save it. Anyways, enough on formatting. Let's head on down to the terminal and let's call python deploy.py. And we can see our terminal printed everything in simple storage file, which is perfect. Now, our Python script has what it needs to actually get started working with our Solidity. Now, something you'll see I do a lot is I save a lot. And if you're looking for some keyboard shortcuts, you can always do Command P, add a little bracket here, and look up keyboard shortcuts reference and click this. And it'll bring you to this keyboard's reference page based off of what operating system that you have. All right, great. So now that we can actually read from our simple storage.sol file, we actually have to compile it. Because remember, back in Remix, every single time we did anything with our files, we had to compile them first. So we need some compiler in Python. Luckily, there is a fantastic Python package called pysulkx that does exactly this. Now, I also want to point out, though, that pysulkx is actually a fork of this package called pysulk. Now, you can still use pysulk. However, I'm going to highly recommend that you use pysulkx instead, as pysulkx is a lot more actively maintained than Ethereum pysulk. We can install it with pip install pysulkx. We could even hit this little copy button, move back on over here, paste it in, and hit enter. Again, I've already installed it, so it's pretty quick for me. The way that we can use it now is by importing it into our Python here. So we'll say from sulkx import compile standard. Compile standard is going to be this main function that we actually use to compile this code. So let's go ahead and compile our Solidity. We're going to save our compiled code to a variable called compiled sol. And this is going to be equal to us calling this compile standard function, but we're going to add a lot of variables and a lot of parameters into this function here. First thing we have to add is a language, which in this case is Solidity. We're going to add in some sources, which we're going to say our sources is going to be simple storage.sol, and it's going to have some content, which is equal to this simple storage file variable that we made. Oh, excuse me. This all has to be in a bracket piece as well. And see, if I hit save here, it auto formats, which is really nice. And another quick tip, you can see how even my brackets are highlighted in these fun colors. If we go down to extensions and look up bracket, you can add this bracket pair colorizer, which will help make the brackets look a little bit nicer, kind of as you see here. You can go ahead and install that as well. Anyways, then we'll add some settings. And a lot of this is a little bit lower level stuff than what you're really going to have to know or use. So I'm not going to go too deep into everything that's actually going on here for now. But in our settings, we're going to choose an output selection, which is going to choose what we output when we compile this. We do a little star here. And in the star, we're going to do another star. We're going to choose our output list. We're going to get an ABI out. That's incredibly important, which we've talked about before. We're going to get some metadata. We're going to get an evm.bytecode. We're going to get an evm.sourcemap. That's pretty much it. Again, I'm not going to go too deep into what this output selection and what these settings are actually doing. But if you want to learn more, you can go to the homepage of pysulkx, scroll down to the documentation section, and read more in the docs on what you can actually put and all the different features that this actually has. The last thing we're going to do is we're going to add a sulk version or Solidity version. We're going to say sulk version equals, and then we'll choose the version that we want to use. So we'll put in 0.6.0. And then what we should be able to do is print out this compiled sol, and we'll see just a whole bunch of really low level stuff. So let's go ahead and run this. We'll run python deploy.py, and you'll see we get this massive object here which has a whole bunch of basically unreadable pieces. But this is a lot of the low-level code that actually gets compiled whenever we use the compiler in Remix or now in Python. Remix actually does the exact same thing. Once we compile something on Remix, you can actually copy the bytecode. If you hit this little copy button and copy the bytecode and come back to your VS Code and create a new file, a keyboard shortcut to create a new file is Command N, and we paste everything, we can see there's a whole bunch of stuff in here. These opcodes are the low-level code that our contract is actually doing, that actually governs how this code works. This is what our written code is getting compiled down to, so Solidity can actually read it and understand what's going on. You'll also see this thing called ABI, which is in Remix, and we're even going to output it right here. We have this ABI thing. Now in Remix, if you hit copy the button on the ABI, come back, create a new file, paste it, you can see we have this long JSON object. This is that application binary interface that we've talked about so much. You can see that it's actually describing all the functions and variables. So for example, we have a function called addPerson, and it takes two parameters, a name and a favorite number. So we have this input section for the function, and we have this section that describes what the function is actually doing. So the name is addPerson, it doesn't have a return type, it's non-payable, and it's a function. And we can see that for pretty much everything in here. This is the lowest digestible way to say, hey, here's where all the functions are, here's what the parameter types are, here's what the return types are going to be, and everything like that. So we're going to close it out for now, though. So this is fantastic. We've now compiled our Solidity. Typically, I usually also like to output it and print it out to a file as well. So to do that, we'll do with open compiled code.json. And this time, instead of reading, we're going to write, and we'll call this as file as well. Instead of doing file.write, we're going to do what's called a json.dump. Compiled sol file. We do need, of course, to import JSON. Also, just to note, I know it says we're using Sulk here, but please use SulkX still. I ended up filming a little bit of both versions, so I did a little bit of a mix and match, but please use SulkX even if you see Sulk. What this line is going to do is it's going to take our compiled sol JSON variable and just dump it into this file here. But it's going to keep it in the JSON syntax, so it's still going to be JSON-y. So now if we run python deploy.py, we'll see we have a new file in here called compilecode.json. The other reason that I wanted to do this was because if I hit Control S, it actually formats this into a readable way. Now again, we can go into these settings here. We can look up JSON, and we can do enable JSON formatter. And this will automatically make it so that we format this JSON so it's a lot more readable. Again, the reason I like to output this is because this ABI is so important and we're going to use it so much that I like to kind of be able to see it and read through it really quickly. The rest of this lower level stuff like EVM and bytecodes and opcodes, we don't really work with so much. However, as you learn more and more about Solidity, you'll probably see more and more of opcodes. So if you really want to learn a lot of really low level stuff, look into opcodes, but for the purpose of this tutorial, we're not going to be going too deep into it. Okay, awesome. So we've compiled our Solidity. We've even stored our Solidity code to this compiledcode.json file. Now what do? We probably want to deploy it and test it out. So how do we actually do that? Well, first, we actually have to get the bytecode. We need the bytecode of the file so that we can actually deploy it. So we're going to do bytecode equals compiled sol contracts simple storage.sol simple storage EVM bytecode object. All right, great. There we go. So now we have our bytecode. We also need to get our ABI. So we need to get the ABI. So what we're doing here when we're typing in all these words like contract, simple storage, is we're walking down the JSON here. So when we say we want to get the bytecode, in this compiled Solidity JSON, we want to go to contracts, simple storage, EVM bytecode. So contracts, inside this contracts JSON, we got to go to simple storage. Inside this simple storage.sol, there's another simple storage. Inside that, there's an ABI, but That's not what we want. We want the EVM. So we're going to scroll down. Aha, we're going to get the EVM. Then what do we want? Then we want the bytecode. Great. And then we want the object. So this is the bytecode of our contract. It's the really low-level stuff that the Ethereum virtual machine, or the EVM, is going to understand. Now, we also need the AVI. When we deploy this to a chain, this is what we're going to need. We're going to need the bytecode and the AVI. The AVI we can, of course, get from this kind of same method here. So to get this, we can do AVI equals compiled sol, same thing, contracts, simple storage.sol, simple storage, and as you can see, we're right here, and then we can just grab this AVI object. AVI. And we can even do print AVI, we'll do Python, develop.py, and indeed, our AVI is printed here. Awesome. So now that we have our two main pieces to deploy this, now all we have to do is deploy it. But the question then becomes is, where are we going to deploy it to? Which blockchain are we going to deploy it to? In Remix, when we were first playing around, we were using a JavaScript VM, or a fake or a simulated environment. We absolutely could, and we absolutely will learn to deploy this to a testnet, because that's going to be the same way that we're going to deploy it to a mainnet. But before we do that, we should learn how to deploy this on a simulated environment or something similar to that JavaScript VM, so it's much faster and easier to test things. And this is where Ganache is going to come to the rescue. Ganache is a simulated or a fake blockchain that we can actually use to deploy our smart contracts to and have it interact like it's a real blockchain. Ganache is going to allow us to spin up our own local blockchain. And it'll look something like this. Now, the user interface is really nice because it allows us to kind of do this one-click blockchain to create our own local blockchain. That means that this blockchain isn't connected to any other blockchain out there, but it'll act like a blockchain. But it'll be a lot faster than us having to interact with a testnet, and we control the entire blockchain because it's only one node. We're the only node. So Ganache, great way to test things quickly. Now, we're going to mainly be working with the user interface, but I'm also going to show you how to work with the Ganache command line. You can really use either one depending on what you want to do, but a lot of the tools actually have built-in Ganache command lines, so it's definitely really useful to learn that as well. So again, Ganache is going to be our simulated environment here. So what we're going to do, once we get into Ganache, we can just go ahead and hit Quick Start. This will automatically upload and get started with our own local fake blockchain. You can even see it gives us some accounts. This should look pretty familiar. It should look very MetaMask-y, right? We have an address here, and each one of these addresses has a private key. In your Ganache, you can go ahead and just click the key and hit Show Keys, and it'll show you the account address and the private key. But of course, these are for development purposes only. Each one of these accounts has a balance associated with it. We can see a mnemonic or your secret phrase. You can see blocks, transactions, and a whole lot of other really useful features here. And it even tells us how to connect to this blockchain. And these are the connecting features that we're going to want to use. Let's learn how to connect to this Ganache blockchain from this user interface first, and then we'll learn how to do the command line version. This is when we finally start working with web3.py. You can just do pip install web3. And now we can start working with web3.py. Right at the top, a little confusingly, we're going to do import web3 from web3. Whoops, and this should be from web3, import web3. Sorry about that. Now, to connect to this blockchain, we choose what's called an HTTP provider. If we look at this Ganache instance, we have this RPC server, which has this URL, HTTP 0.0.0.854. This is the URL that we're going to use to connect to this blockchain. In Remix, we're actually using our MetaMasks directly to connect to the blockchain. However, we want to connect directly to our simulated, our fake blockchain right here. So what we're going to do is we're going to do W3 for connecting to Ganache. W3 equals web3, web3.http provider of HTTP 0.0.0.0 and it was on port 845. Port 845. Now, with everything that we show you, you're probably going to want to get really familiar with the documentation because even after being a pro, you're going to want to use it more and more. If you want to learn more about other providers, you can go to the providers page of the documentation. The next thing that we're always going to need as well is we're going to need the chain ID or the network ID. What is the ID of this blockchain? And for Ganache, it's 1337. It's supposed to be a funny LEET reference. So we'll do chain ID equals 1337. Now, we're also going to need an address to deploy from. We can go ahead and grab one of these fake addresses in here to work with. Similar to how in Remix, when we were working with the JavaScript VM, we were given a bunch of fake addresses. We're doing the same thing, but with Ganache. And then we're also, of course, going to want a private key. We need the private key, of course, to sign our transactions. So we'll do private key equals this. Now, just note, whenever you import a private key in Python, you need to add an OX to the front. Python is always going to look for the hexadecimal version of the private key. Awesome. Now we have all the parameters that we need for interacting with and connecting to our Ganache local chain. It's time to finally deploy our simplestorage.sol contract. Let's do it. So to create a contract that we're going to deploy with web3.py, we're going to do simple storage. We're going to call this variable w3.eth.contract. And we're going to give it ABI equals ABI and bytecode equals bytecode. Great. Does this mean we've deployed it? Well, no. This just means we have a contract down. So we can do print simple storage, and you'll see if we run python deploy.py, you'll see we have a new type here, class web3.utils.datatype.contract. This is another type that if you want to learn more, you should definitely check out the web3.py documentation. So we have a contract object. Awesome. How do we actually deploy this? Well, we need to actually build our transaction. Because again, whenever we interact with the blockchain, whenever we make a state change, and in this case, we'd be deploying a contract, we're going to make a state change. So we first need to build a transaction, sign a transaction, and then send a transaction. And to do that, we need to talk about that nonce thing again. Remember way back in our blockchain demo, when we used a nonce to solve the answer to that really difficult mining problem? Well, the definition of nonce is just a word coined or used for just one occasion. And in cryptography, it's an arbitrary number that can be used just once in a cryptographic communication. So this nonce that's used to find the answer is going to be different from another nonce that we're actually going to need to make our transaction. See, if we look at our MetaMask and we look at our activity, and we look at one of the transactions we've made recently on Etherscan, if we scroll down, we'll see nonce here as well. This nonce is the number of transactions that our account has actually made. Every time we make another transaction, our transaction is hashed with a new nonce. This is what's going on behind the scenes with our transaction. And we need this to send our transaction. We can actually get our nonce by just grabbing our latest transaction count. Get the latest transaction. We can do nonce equals w3.eth.get transaction count. And we'll put in my address. This will give us the number of transactions, and it'll effectively give us our nonce. We can even test it out with a print. Python deploy.py. We can see that the answer is 0, because on our local blockchain, this address that we're using hasn't been used before. We can even go to the transactions tab, and we can see that there are no transactions that have ever occurred on our local blockchain. Now, to deploy this contract, we need to make a transaction. Remember, everything that we do, every time we change the state of a blockchain, we're going to do it in a transaction. Let's create a transaction object. To do this, we can do transaction equals simple storage, which again is this contract object, dot constructor dot build transaction. Now, as you might have pointed out, our simplestorage.sol doesn't actually have a constructor. Every contract technically has a constructor. This one's is just blank. We're not telling our simplestorage.sol to do anything. We saw back in our fundme example that the fundme example does have a constructor. So now we want to put in some parameters for this transaction. In web3.py, we always have to give at least a couple of parameters. We always have to give the chain ID, which we already got from above, which is 1337. So we can just do chain ID. We need a from address, in this case, my address. And then we need a nonce, which in our case is just nonce. Great. Now we have a transaction object. Let's even print this out and see what it looks like. Whoa, what's this? We can see there's even more parameters in here than just what we made. So we have value, which is the Ether or the Ethereum that we're going to send. We have gas. We have our gas price, which we could arbitrarily set if we'd like. We have the chain ID. We have from address. We have the nonce. And then we have this giant data object. And then 2 is just empty because it's sending it to the blockchain. This giant data object here is encompassing everything that's happening in this simple storage.sol. Now, that's just a transaction, and anybody could actually send this transaction as long as it's signed by them. So we have this transaction, but we need to sign it from somebody. Since we're sending it from our address, our private key is going to be the only key that's going to work to sign this. Remember back when we were talking about public and private keys, we right now have a message that is defining how to deploy simple storage, but it's not signed yet. So we're going to need to use our private key to sign it to create this unique message signature that we're the only ones that can create the private key, but anybody else can verify that it was us who signed it. So now signed transaction equals web3.eth.account.sign transaction, and the parameters it takes are going to be transaction and then private key. We're going to say the private key equals private key. Because above, we've actually gone ahead and added our private key in here. Now guys, a really, really important note about putting your private key in your code. This is really bad practice. If you push this to source or you push this to GitHub, somebody else can see your private key and steal all your funds. So we don't want to hard code our private keys in our code like we're doing here. So let's take this time to talk about environment variables and how to set them. Environment variables are variables that you can set and that we set in our terminal and in our command lines. The following is a way to set an environment variable in macOS and Linux only. Don't worry, we'll show a way to make an environment variable in Windows as well. You can set an environment variable by running something like export private key equals, and then adding whatever variable that you want. Now, if you type echo $ private key, this variable actually shows up. To set environment variables with Windows, the process that we're going to do is actually a little bit different. I've left a link in our GitHub to actually set environment variables in a Windows setting. And we've left a couple of really helpful links for working more with environment variables. You should definitely check them out. It's important to note that this export method that we're doing here for creating environment variables only works for the duration that our shell is live. So if we were to close out of our shell and then reopen it, our environment variable that we set would be gone. So we'd have to rerun that export command. We're going to show you a way to set environment variables so that you don't have to keep doing that. Now, it's also not great to have it in plain text on your computer. However, it's a lot better than hard coding it into our script here. Now, remember, if you're using an account that has real money in it, which I highly recommend you do not do, don't send this environment variable or this private key or any of this code anywhere, because then people can steal all your funds. Once we move to Brownie, we'll show you a more effective way for private key management. But for now, be cautious here. But if you followed along and set up a brand new account that has no real money and only test that money in it, then great. Who cares? Because it's test and it's fake money anyways. I think I've talked about it enough. Anyways, let's get back to it. We can actually access this environment variable in Python using os.getEnv. We just need to import OS. And now we can access our private key in our script without actually hard coding it in. Let's see what happens if we do print private key, python deploy.py. You can see our Python script was able to pull our private key from our environment variable. The other thing that we can do is create a .env file. A .env file is typically where people store environment variables. It's important to not push these to source if this is what you're going to do. In this .env file, in Python, we can just do export private key, and then same as what we did before, add the 0x at the start, and then private key. So we could put 100 environment variables in here. Export some other var equals 7. If you're going to do it in this way, please, please, please always set a .gitignore and make sure .env is in here. This will help make it harder for you to accidentally push your .env folder or your .env file to GitHub. Python actually has a way of loading directly from a .env file without having to export our environment variables or run source.env or export or really anything. And we can do it with this python.env package. If we close our shell and then reopen it, if we run echo some other var, we're going to get none here. And in fact, if we run python develop.py, when we print this environment variable, we're going to get none. However, we can use this .env to have it pulled directly from our .env. So we just do pip install python.env. I've already downloaded it, so it just says requirement already satisfied. And then what we can do at the top of this, we can do from .env import load.env, and we can run a load.env function right at the top. This load.env looks for this .env file and automatically imports it into our script. So if we run this now, you'll see that the environment variable was successfully imported into our script, and now we can use it. So let's use it, for example, with our private key. Private key equals os.getEnv. Private key. Now we can even print it out just to test. We'll run our script, and awesome. We can see our private key is being successfully pulled in, and we didn't hard code it into our application. All right, let's get back down to our signed transaction here. Now let's go ahead, print this out, and take a look at what this looks like. Now we can run our script, and great. What we see here is an example of a signed transaction. Remember, this is exactly what's happening when we were looking back at public-private keys. We are signing a transaction that is actually deploying a contract to the blockchain that anybody can easily verify. All right, so we finally have our signed transaction. Now we want to send this to the blockchain so it actually can deploy. Let's send this signed transaction. We can do transaction hash equals web3.eth. Here's a little helpful tip. If you see this little box underneath with suggestions show up and you just hit tab, it'll auto-complete the rest of your text here. .send raw transaction, and we'll give it our signed transaction dot raw transaction. This will send our transaction to the blockchain. Now, if we look at our local Ganache and we look at transactions right now, it'll be empty. But let's see what happens when we run this script. Okay, so we didn't print anything out, but if we go to our Ganache, we can see that a transaction actually did go through. It was from the address that we put in here. We created a contract at this address. This is how much gas it used, and this is how much value was sent with it. We can even click on it to see more information about this. Now, this is the other advantage of doing this locally, is that the transaction automatically went through. We've sent our first transaction to a local blockchain, and this transaction is deploying a contract. Great work. You can already see how much faster this is than working with a testnet. One other thing that's really good practice whenever sending a transaction is we wait for some block confirmations to happen. So we can do transaction receipt equals web3.eth.wait for transaction receipt tx hash. This will have our code stop and wait for this transaction hash to go through. Awesome. So I just ran it again. And if we go to transactions, we can now see that there are 2 transactions here. And our code waited a little bit longer for this one to complete. So, of course, we've deployed a contract, but how do we actually interact and work with the contract? Let's start doing that. So when working with contracts and we're working with on-chain, whenever we work with a contract, we always need 2 things. We need the contract address and the contract ABI. Oftentimes, if you're looking for a specific ABI of a type of contract, you can usually just Google it. So we need to make a new contract object to work with contracts. Let's go ahead and create this simple storage contract so that we can actually interact with it. So we'll do simple storage equals w3.eth contract. Now we need our address, which we can get from Ganache, but that might be a little bit hard to always be checking the blockchain for a transaction. It's actually also in this transaction receipt. Address equals transaction receipt dot contract address. And then, since we've compiled this, we also have our ABI already. ABI equals ABI. Sometimes you'll see people have a file called abis.py or abis.json or something like that, and they'll load ABIs in directly from there. And great, now that we have the address and the ABI, we can start interacting with this contract exactly as we did in Remix. So let's do a print statement to get that initial value that is returned from our retrieve function. Remember, it should be initialized to 0. So if we do print simple storage dot functions dot retrieve, let's see what happens here. Huh? What's this? We get this function retrieve bound to in these parentheses here. So what's going on? When making transactions on the blockchain, there's actually two different ways that we can interact with them. We can interact with a call, or we can interact with a transact. When we use a call, this is just to simulate making the call and getting a return value. Calls don't make a state change to the blockchain. And it's similar to how in Remix, we would call these blue buttons and nothing on the blockchain would actually change. We can actually also call these orange buttons or these non-view functions and just not actually make a state change. Remix defaults these blue buttons to be calls and these orange buttons to be transacts. In Python, we can actually pick which one we want to do. A transact call is when we actually make a state change. And this is when we actually have to build a transaction and send a transaction. You can always just call a function no matter what that function is, but just keep in mind you won't make a state change. You can also always transact on a function even if it's just a view, and this will attempt to make a state change. Something like retrieve, even if we transact on it, it won't make a state change. So for something like retrieve, where we don't actually want to make a state change, we just use the call function. So we'll just do .call. Now, if we try to run this, you'll see we do get the 0 because now we're actually calling this transaction. Awesome. So now we have our initial value for our retrieve function. Let's keep going. Let's try to update this favorite number using this store function. This, we'll just keep in mind, is our initial value of favorite number. We know that this store function is orange and will actually make a transaction, but if we wanted to, we can even just use call on it. We'll do simple storage .functions .store, and we'll put that 15 in here, .call. Let's see what happens when we send this. You can see it returned a blank. That's because this store function has no return type. If we give this returns uint256, and then we say return favorite number, and now we go back here and we run this again, you'll see now that we get a 15 back. If we go to Ganache, you'll see that we keep making a whole bunch of different contracts, but none of these are contract interactions. That's because when we call a function, we just simulate working with it. If we call retrieve again right afterwards, you'll see that it's still 0. It's because calling is just a simulation. Now let's delete all that. So let's actually build a new transaction to actually store some value into this contract. Since we want to make a transaction, we got to go through the same process as when we deployed this contract. Let's first create a transaction. We'll call it store transaction equals simple storage .functions .store, and we'll give it some number, in this case 15, and then we have to do .build transaction, and we'll put those same pieces in here from before. We're going to have chain ID be the chain ID, we're going to need from, give me my address. Nonce is going to be the nonce plus 1. We're going to need to do nonce plus 1 because we actually used this nonce already when we create our initial transaction. Remember, a nonce can only be used once for each transaction. So this transaction is going to have a different nonce than the nonce we use to deploy the contract. Now that we have the transaction, let's go ahead and sign it. We'll do signed store tx, and we'll do web3.eth.account.sign transaction store transaction, and then private key equals private key, and we'll go ahead and save. Then, of course, we need to send it. So we'll do transaction hash equals w3.eth.send_raw transaction signed store transaction .raw transaction. And let's grab that transaction receipt again by doing transaction receipt equals w3.eth.wait for transaction receipt. And actually, let's call this send store tx. That wait for receipt, send store tx. Awesome. It looks like we're following the same steps here as we did above. We created the transaction, we signed the transaction, and then we send the transaction. Down here, we create a transaction, we signed the transaction, we sent the transaction, and then we waited for the transaction to finish. So let's run this. All right, great. We still have this print function printing out the current value of retrieve. Let's go over to Ganache and see if there's anything different here. There is. Instead of all these contract creations here, we now have a contract call. We can see there's some transaction data that was sent, a different amount of gas, same gas prices. However, this actually updated and sent the transaction to our blockchain. Now, if we call this retrieve function again, this should print out our newly updated value, which in this case was 15. Let's go ahead and run Python deploy.py, and we can see it started at 0, and then it turned to 15. Awesome. We've made our first state change to a contract that we've deployed on our local blockchain. Great work. Sometimes it's nice to put some lines in here to tell you what's going on, to make it a little bit more clear. So I'll put something like deploying contract, ... right before we deploy our contract. After we do it, I might do deployed. Then, right before we update our contract, we'll print out something like updating contract. And then, right after it's done, maybe something like updated. Now, if we run this now, you'll see as this goes along, we'll get these things printed out saying deploying contract, contract, deployed, updating contract, updated. This will make those moments when waiting for these contracts to actually finish a lot easier. You're doing fantastic. So Ganache user interface is really nice because we can see a lot of things that are going on here. However, it's a little tricky to do a lot of programmatic stuff. Oftentimes, engineer will use what's called a command line interface of Ganache instead of the UI. So we're going to go ahead and close this out, and we're going to use the Ganache CLI instead of that user interface that we just saw. And this is what Brown is going to use on the back end when we move to Brownie. Let's learn how to actually do that. So in order to use the Ganache CLI or command line interface, the first thing that we need to do is download Node.js. Yes, I know this is a Python video. However, we do need to install Node.js to work with the Ganache CLI. You can come to this download page and choose your operating system and download it accordingly. We have a link to a video showing you how to do this in the GitHub. You'll know you've done it right if you can run node -- version in your command line and you get a version. It might be 12, might be 14, might be something else, depending on what version you downloaded. Next, we're actually going to install Yarn. Yarn is a package manager similar to pip and will allow us to actually download pieces and packages like the Ganache CLI from the package repository. We can install it with npm install --global yarn. And you'll know you've done it right if you can run yarn --version in your command line, and you get the version outputted here. Then we want to install the actual Ganache CLI. We're going to be installing it with yarn. So to install this, we're going to do yarn global add Ganache CLI. This will install our Ganache CLI as a global command in our terminal. We can test to see if we've done it right. If we can run Ganache CLI --version. Perfect. We now have the Ganache CLI. Let's spin up a Ganache chain with the CLI. If you have your Ganache UI open right now, please close it. Otherwise, it'll conflict. So to run a local blockchain from the command line, all you need to do is run Ganache CLI. And the node will start running directly in your terminal. If you scroll up, you can see a lot of familiar pieces. We see the available accounts, just like on the UI. These are the different addresses. And then we see a whole bunch of different private keys. This Ganache spins up with a bunch of random addresses and random private keys. If we wanted to always spin up with the exact same private keys so we don't have to update our private key every time, we can do Ganache CLI --deterministic. This way, we'll always get the exact same private keys and the exact same addresses. You can check out the documentation to see a bunch of other flags that you can use to run this. And you can see it's listening on 127.0.0.1. 127.0.0.1 is also known as the loopback address or localhost. Now to work with Ganache in the command line, all we need to do now is update our private keys and our addresses. Let's also update the HTTP provider, since now we're going to be looking at the loopback address. For my address, we'll scroll up to this top address here, and we'll place it in. And for our private key, we're going to copy this and put it into our .env file. It already has the OX at the top here. Great, now let's open up a new terminal. You can open up a new terminal by hitting this plus button here. And you can flip back and forth by hitting this drop down and flipping back to the Ganache terminal. Now let's go ahead and run Python deploy.py. We can see the exact same output as we got when working with the UI. And if we flip over to the command line, we can see we've made a whole bunch of different calls to our blockchain. Each one of these calls is a specific JSON RPC call to our blockchain that we're making to interact with it. We can see information about the transactions that we sent. This one creates our simple storage contract. This one updates our simple storage contract. And great, you now know how to work with the Ganache CLI and the Ganache UI. Fantastic. So how do we actually deploy this to a testnet or a real network? When we're working with Remix, all we had to do was switch to injected Web3, and we used our MetaMask as our blockchain connection. Well, in our script here, we don't have MetaMask natively with our script. So we need some way to connect to the blockchain. We can see that when we're connecting to our own local blockchain, we just use an RPC URL that connects to our local blockchain. To connect to a testnet or to a mainnet, we can actually do the exact same thing. All we have to do is swap this out with the URL that connects us to a mainnet or a testnet. We can also run our own blockchain node, similar to how we're running our own local blockchain node. We can run a node that actually connects to a real blockchain. However, it's not always practical or really easy to do this. So sometimes we want to use an external or a third-party client that actually will run our blockchain for us. Let's learn a little about Infura. Infura.io is an application that will give you a blockchain URL for you to connect with, for you to run whatever you want to run. And you can get started for free. Let's go ahead and register. Then we just check our email, confirm email address, and awesome. Now we're inside of Infura. There's a couple other services out there that you can also check out, like Alchemy, which is another fantastic blockchain as a service platform. Infura is a freemium service. It starts out as free. If you make too many API calls or too many calls to the URL, they'll start charging you. But we can create a project for free for now. Let's go ahead, hit the Ethereum tab, hit Create Project. We'll call this Free Code Camp Brownie. Hit create. Now we'll have a whole bunch of project keys and project secrets. We also have this endpoint section as well. This is how we're going to be deploying to the different networks. We can see we have an Ethereum mainnet connection, as well as Ropsten, Kovan, Rinkeby, and Gorilli testnets. There's also Polygon in here as well. Since we want to test and deploy to a Rinkeby chain, we can go ahead and move to Rinkeby. And then we can copy this URL. Back in our application, all we have to do is swap this out for the new URL. We also have to change the chain ID, our address, and the private key. If you ever are confused as to what is the chain ID of the chain that you're working on, you can always check this chainid.network, or you can usually ask somebody. Let's look up Rinkeby. We see the chain ID is 4. So we'll grab 4 and we'll place that in our script. Now, this address and the private key that we gave it, aren't going to have any testnet Rinkeby in them. So we need to go in our MetaMask and grab the address, place that in for address, and then account details, export private key, type in our password, and grab the private key. Go into our .env file, leave the 0x, and replace the rest with our private key. Since I have my private key stored as an environment variable, I need to then run source.env so that my private key is now updated. The reason we're using this is because, again, since we're making transactions to a testnet, we need some testnet ETH. All right, so now we have everything updated for deploying to Rinkeby. Let's go ahead and run this now. As you can see, it's going a lot slower. This is because we actually have to wait for the contracts to get mined and for everything to happen on the testnet. Deploying to a testnet will result in nearly the exact same experience that you'll get when deploying to an actual mainnet. So it'll take a lot longer, but you can see we got the exact same responses here. Now, if we take this address and we go to the Rinkeby Etherscan, we can verify what just happened. We can see that 38 seconds ago, we made this transaction, and then 23 seconds ago, we made this transaction. We can look at all the different details of this transaction that we just made from our Python script. We can see it even tells us we created a smart contract, and then we made this call, which called this store function on this contract. Whew, we've learned a lot so far. This is fantastic. Now is a perfect time to take a break and take a quick breather and reflect back on what we've just learned. We've learned a lot about Python, deploying to our own local blockchain, deploying to a testnet, and deploying to a mainnet, working more with private keys, creating transactions, signing transactions, and then sending transactions. Now, as you can see, there's going to be a lot to actually managing all the contracts that we work with. Having to write our own compile code and our own storage code is going to take a lot of work. And what if we wanted to interact with one of the contracts that we deployed in the past? Well, we'd have to keep track of all those addresses and manually update our address features here with an address. Maybe we didn't want to deploy a new contract every single time. Maybe we wanted to work with a contract that we've already deployed. What if we want to work with a whole bunch of different chains? What if we want to work with Rinkeby and mainnet and our own local network? There seems to be a lot to manage here, and we still haven't even talked about writing tests. This is where Brownie is going to come into play. Brownie is currently the most popular smart contract development platform built based on Python. It's used by DeFi giants like Yearn.finance, Curve.fi, and BadgerDAO, each having billions of dollars currently locked in value. And the reason that we learned a little bit about Web3.py first is because Brownie heavily relies on Web3.py. So let's do all this again, but in Brownie, and we'll see how much easier it is to actually interact with. In our shell, let's go back one directory, and let's make a new one. We'll call it Brownie Simple Storage. Now, another really cool trick that VS Code has is instead of us having to go to File and open up this folder in this Explorer here, what we can do is we can type code and then type the directory that we want to work with. In our case, this directory. So we can just type code dot. And we'll get a new VS Code pop-up inside of this Brownie Simple Storage folder. Let's get learning about Brownie, and this is where you're going to spend the majority of your time moving forward. Brownie is incredibly powerful and makes our lives fantastically easier. So get ready to learn one of the most powerful tools in the smart contract developing ecosystem. Let's go ahead and open up our terminal. And let's get started installing Brownie. It's recommended to install Brownie via pipex. Pipex installs Brownie into a virtual environment and makes it available directly from the command line. Once installed, you'll never have to activate a virtual environment prior to using Brownie, which is really good. To install it with pipex, we can go ahead and run python -m pip install --user pipex. Once we've run that, we can then run python 3-m pipex ensure path. Then we'll want to close the terminal by hitting the little trash can and then reopen it. And then we just need to run pipex install brownie. I've already got it installed, so that's why we see this here. And then just one more time, we're going to close and reopen the terminal. You can tell you have Brownie installed correctly if you run brownie -- version. And you get some output that looks something like this. Or you just run straight up Brownie, and it'll output a bunch of commands that we can run. Let's create our first Brownie project. We're going to be using the exact same simple storage code that we just went through, except for we're going to use it in Brownie. This is going to make our lives a lot easier when working with simple storage. To create a sample folder with everything we need with Brownie, we can just run brownie init. And we will get a new Brownie project initialized in the directory that we're currently in. If you type ls, you'll be able to see all the folders that are created, or you can just see them on your side panel in VS Code. Let's talk really quickly about what each of these folders is going to do. The build folder tracks a lot of really important low-level information. It's going to track any interfaces that we're working with or deploying. It's going to keep track of all of our deployments across all of the different chains, so we no longer have to manage that ourselves. And it's going to store all of the compiled code. Remember how in our simple storage code, we actually saved everything to this compiled code.json? Well, Brownie is actually going to do all of that for us into this contracts directory, so we can always reference it later. This contracts directory outside the build folder is where we're going to put all of our contracts. Brownie knows to look inside of this folder when looking for new contracts to compile, deploy, or anything else. Interfaces is where we can save and store different interfaces. Remember how when we were working with Chainlink, working with interfaces makes it really easy to interact with a blockchain application. Reports are to save any type of report you run. Scripts are we can automate tasks like deploying, calling different functions, or really anything we want. And then we have a test folder, which is incredibly powerful and we're going to be using a lot. We also have git attributes and git ignore, which are helpful when working with version control like Git. So let's go ahead and start working with Brownie and really understand what's going on here. So let's go ahead and add our simple storage contracts to the contracts folder. So in here, we're just going to make a new file. We'll call it simple storage.sol. And I'm just going to copy and paste the code I have from the simple storage that we've been using this whole time. Let's go ahead and save that with Command S. Okay, great. Now that we have our contract in here, we can already start working with Brownie and even compile this code without even having to write or work with our own compiler. All we need to do is run brownie compile. Brownie will automatically read the version of Solidity and then store all of the compile information in this build folder. So if we go to contracts, we can see we have a simple storage.json, and there's a lot of familiar pieces in here. For example, we see the ABI opcode section, which is the low level language. We'll see a PC map and we'll see a lot of useful information. And great. Obviously, deployments and interfaces are still empty. So great, we've already compiled our smart contract. So how do we actually deploy this to a blockchain? To do this, we do have to write a script, which will allow us to do whatever we want. So we're going to create a new file, and we're just going to call this, similar to last time, deploy.py. This is where we're going to define working with and deploying our code. Brownie can run scripts by running brownie run. In fact, if you want to take a quick minute to familiarize yourself with all the different commands that Brownie has, just run brownie and you'll see we can do a lot of different things. We can do brownie init, which will create a new brownie project. We will do brownie bake, which allows us to pull from the brownie mix, which we'll talk about later. We can compile, we can go into a console, test run. We can do a lot of wonderful things in here. If we do brownie run, it'll run a script for us, and we can define that we want to run this deploy. All we have to do is add a def main. So def in Python is the way to define a function. We're going to call this function main. And for now, let's just say print hello, and we can run brownie run scripts deploy. And as you can see, it automatically does this launching thing. So Brownie defaults to always working with a local Ganache CLI blockchain. It's running the exact same command that we ran earlier, and it has a bunch of different flags, like accounts 10, a certain hard fork, a certain gas limit, etc. So at the beginning of all of our scripts, if we don't give Brownie a network to use, it'll spin up a local ganache, and at the end of the script, it'll tear it back down. Typically, what I like to do is actually put all of the logic of our deployment in its own function. Def, deploy, simple storage, and we'll do pass for now. And then our main function, we can just call deploy simple storage. Now, in order to deploy our contract, let's look back at our Web3 Pi version of deploying this and see what we did. So first, we compiled it. Great, Brownie does that automatically. Then we dumped it to a file. Great, Brownie does that automatically. We got a bytecode and an ABI. Great, Brownie does that automatically. We added a local blockchain to use. Great, Brownie automatically spins up a local ganache. We'll learn how to do testnets in a little bit. Aha, we do need an address though and a private key. So how do we actually get our private key, get our account into Brownie? Brownie has an accounts package that actually natively understands how to work with accounts, and we can import it into our script here. So we can do from Brownie import accounts. And with this accounts keyword, we can add an account a number of different ways. If we're going to work with our local chain, as you see here, the Ganache CLI will spin up 10 fake accounts for us. And Brownie automatically knows that we can work with that account. So we could do something like account equals account 0, and then just do something like print account. So we're going to take the account that's spun up at the 0th index, because this accounts object is just an array. So if we run this now, Brownie run scripts, deploy, it's going to spin up us an address and a private key that we can just work with without having to define a private key or do anything. It does all of that for us, which is fantastic. We do, of course, still want to know how to add our own private keys so that we can work with a testnet. So this is great and works when we're working with a development network or working with Brownie's automatic Ganache CLI. If we want to work with a testnet though, we have to do something else. Another way to add your accounts in Brownie is to use the command line and actually add them natively into Brownie. We can do Brownie accounts new, and we'll give it a name, free code camp account. This will then prompt us and say, enter the private key that you wish to add. Let's go ahead and grab our private key from MetaMask, account details, export private key, put your password in, grab the private key, and then we just add OX and paste it in. Brownie will actually password encrypt your private key in this way. So we'll give it a password. And now we have a new account natively integrated into Brownie. To see it, we can do Brownie accounts list, and you'll see that we have a free code camp account with this address and also a testing account. I made this a little bit earlier. We can get rid of it by running Brownie accounts delete testing. Helpful terminal tip time. So if you hit up or down on your keyboard, you can actually toggle through the history of the commands that you've written. So if you hit up, it'll actually bring you to the most recently run command, which can allow you to run previous commands a little bit faster. And if we run Brownie accounts list again, we'll see it's now just free code camp. If we want to work with this free code camp account that we've added to Brownie via the command line, we can get it with account equals accounts.load free code camp account. And then we can do print account. Let's run this script again. This time when we run the script, it's going to ask us for the password. We need to enter the password to decrypt the account because right now it's password encrypted. So we're going to type in the password and it's going to go ahead and execute with our unlocked private key. We can see the address it printed out was right here. And if we copy the address and we go back, we can see that that is correct. Now, if we're going to talk about safety and you want to safely secure your keys, this is one of the safer ways to do it because it's not going to store it in Git. You're not going to accidentally push it up to GitHub or show it to anybody, and it's going to be password encrypted. This is going to be one of the ways that I highly recommend you store your keys. Oftentimes, you're going to want to do a mix of working with the local Ganache ones and your own keys, and we'll learn how to flip back and forth between them in a little bit. Now, the third way that I like to use is still, again, using an environment variable script. Oftentimes, it's really easy just to have your private key be an environment variable. This way, you won't have to keep putting the password in every single time you run a script. So it's a little bit less secure. And just another tip for myself, I never put my private keys associated with wallets that have real money in them as environment variables or in a .env file, just in case I accidentally do something really stupid. I don't trust myself enough. So I'm gonna highly recommend that whatever private key that you use and you store as an environment variable here, always have it be just kind of a test account that you're gonna use to test things. And then for some of your more serious accounts, that's what you'll use the encryption for. So let's go ahead and create an environment variable file. So we'll do a new file, call it .env, and we'll do export private key OX this. Now we have a private key set as an environment variable. So Brownie has an additional feature that allows us to easily work with environment variables in an environment variable folder. We can tell Brownie to always pull from our .env file in a Brownie config.yaml. This is a special file that Brownie always looks for to grab information about where you're going to build, where you're going to deploy, and where you're going to grab things. In this config, all we need to do is add .env and set .env. This is telling Brownie, hey, when you run scripts, grab the environment variables from the .env file. And what we can do is after we import OS, we'll do account equals accounts.add os.getEnv. This is how we get that environment variable private key. Then let's just print out that account and see if we did it right. Brownie run scripts deploy.py. And great. All right, great. So this seems to work perfectly, but I like to make this method even more explicit. So we're going to take this version that we just learned and improve it. In our Brownie config, we can actually add more information about what wallets we want to use and when we want to use them. What we can do is we can add a wallets section and add in here a from key section and then add that environment variable, private key. In your YAML file, if you surround a string with $sign and some curly brackets, it will automatically get transformed into the environment variable. So if we go back to deploy, we can actually change this. We can grab right from our config file. So we'll do from Brownie import accounts, config, and instead of using OS, we can do accounts.add config, and then we'll do wallets, since that's what we're defining right here, and then from key, wallets, from key. And this will do the exact same thing as our os.getEnv. The reason that this is better is because now we have one canonical place where we're always going to pull our private key from, instead of having to go through all of our scripts and update it based on whatever we change an environment variable. Now let's try this out. Brownie, run, scripts, deploy. And great, we see our address printed here. For now, let's just stick with using accounts 0, since we want to just use the account that Brownie makes for us with Ganache. Now, Brownie is really intelligent, and we can actually go ahead and import a contract directly into our script. In a web3.py version, we opened a contract and read from it, and that's how we were able to interact with it after we deployed it. In Brownie, what we can do is from Brownie, import, and then just the name of the contract, simple storage. Then we can do simple storage.deploy. And this is how we're going to deploy it to a chain. Anytime you deploy to a chain or you make a transaction, you always need to do a from. And then say who you're going to be deploying from. What's the account that's going to be deploying this? As you can see, this step of just deploying is much quicker than what we did in web3.py. In web3.py, we had to get the bytecode and the ABI, then we had to get the nonce, we had to create the contract, we had to create the transaction, sign the transaction, and then send the transaction. Remember how I said before, you could either make a transaction or a call? Brownie is smart enough to know whether or not what you're doing is going to be a transaction or a call. In this case, since we're deploying a smart contract, Brownie's smart enough to know that, we want to make a state change, so let's make a state change. It'll return a contract object. So we can just add print simple storage, and we'll see what prints. So let's run this. Brownie run scripts deploy.py. Awesome. So what happened was Brownie, again, per usual, it launched a local Ganache chain, and then it sent a transaction to deploy simple storage. And it says simple storage deployed at, and then the address it was deployed at. And we can see how much quicker this is to actually deploy. Now let's go ahead and do exactly what we did with web3.py. Let's call this initial retrieve function, and then we'll update it with a new value of 15. But we'll do it in Brownie now. Remember, here's how we did it back in web3.py. In Brownie, what we're going to do is first, we're going to do stored value equals simple storage dot retrieve. Now, since this is a view function, we don't have to add from account in here. Again, Brownie is intelligent enough to know if this is a call or a transaction. And we know that retrieve is a view function, so we know we don't actually have to make a transaction here. Then we can print out the value of stored value. Print stored value. Let's go ahead and try this. Great, we get 0 right here. Perfect. Now let's try updating this. So we can do transaction equals simple storage dot store. And in here, we'd want to do 15. But remember, since we're doing a transaction, in Brownie, we always have to add who we're going to transact from. In this case, we're going to do from account. Similar to web3.py, we can do transaction.wait for how many blocks we want to wait. And then let's call that retrieve function again to see if it's been updated. So we can do updated stored value equals simple storage dot retrieve. And then we can print the updated stored value. And if we run this, we now see we have two transactions here. One that deployed our original simple storage contract, and we called the retrieve function and we returned 0 here. Then we updated with our store function, and then we call retrieve again, and we see we did indeed update it to 15. You see how much smaller and easier and more intuitive this is in Brownie, and how much our lives are going to be much better. Awesome. Now you've learned how to deploy to a local chain. Now running these scripts is fantastic, but we need a way to actually automate that our contracts are doing what we want them to do. We don't want to always have to manually check that all of our stuff is doing what we want it to do, right? We don't want to have to manually check that 15 is actually updating appropriately. This is why running tests are so important, and automating your tests is going to be crucial to becoming a successful smart contract developer. Now, I do want to point out that you actually can write tests directly in Solidity. And this is a great way to actually test your smart contracts, is to learn how to do it right in Solidity. However, a lot of the professional developers code their tests in the smart contract development framework language, like Python or JavaScript. Doing it in this way allows you to get a lot more flexibility and customization with what you're doing with your smart contracts, and not being confined to whatever only Solidity has. So let's go ahead and learn how to actually write our smart contract tests in Python. This is what this test folder is for. So we're going to create a new file called test simple storage.py. Make sure you do add test to the front of these, because this is the syntax that PyTest is going to be looking for. And then in our test, we can actually set it up the exact same way we set up our deploy function. We can do from Brownie import simple storage and accounts. Then we can start defining our tests. We want to test to see that when we deploy our smart contract, that it gets started off with 0 in that retrieve function. So we'll create our first test. We'll do def test deploy. And typically, testing in smart contracts, or testing really in anything, is going to be separated into 3 categories: arranging, acting, and asserting. We're going to bounce around and be a little bit loose with this definition for the duration of our tutorials here. However, keep in mind that typically this is the setup that you want to use. Later on, in one of our later smart contract examples, we're going to go through a much better testing setup. So in our arrange stage, we're going to set up all the pieces that we need to get set up. So first, we're going to grab an account. We're going to say accounts equals account 0. And this is really all we need to do to start getting set up. Now, for our acting stage, we're going to deploy a simple storage contract, exactly as we did with deploy. So we're going to do simple storage equals simple storage dot deploy from account. Then we're going to get our starting value. Starting value is going to be equal to simple storage dot retrieve. And we're expecting this to be 0. So then all we have to do in our assert stage is we have to run assert starting value equals expected. So let's recap this. In our arrange stage, we're just getting our account so that we can actually make contracts. Then in our act stage, we're going to deploy this simple storage smart contract. We're going to call the retrieve function to see what its starting value is. And we're going to compare to see if that starting value is what we expect. And we expect it to be 0. We can then test this with Brownie test. And per usual, Brownie is going to kick off a Ganache CLI, and then it's going to test this. For every test you have, you're going to get a little green dot. And we're going to say 1 passed in 1.86 seconds, which is perfect. If we had expected to be 15 and we ran Brownie test, we should get a fail here. Awesome, and that's exactly what we got. Now let's go ahead and test updating this with 15 and see if it works as we want it to. So we can do a new test in here. We'll do def test update thing storage. And we'll do those 3 phases: arrange, act, and assert. In our arrange, all we need to do is get our account from account 0. And in this one, arranging is also going to be deploying our smart contract. Since this is really just part of the setup and not the act that we're really testing. Now in our act, we're going to add expected to be equal to 15, and we're going to run simple storage dot store expected and then from account. You'll notice this is nearly exactly the same as this deploy function here. Now, same as last time, all we have to do is assert expected equals simple storage dot retrieve. We're saying we want to store 15 in our smart contract, and then when we call our retrieve function, it is stored correctly. So let's go ahead and run Brownie test. Awesome, we can see 2 dots here. This means 2 have actually passed correctly. That's great. Now I do want to quickly show you a couple of useful tips that I pretty much always do when I'm running my tests. If you want to test just one function, you can do -k. Brownie test -k, test updating storage, and we will only test this test updating storage. We can run Brownie test -pdb and add something wrong in here, like 5 equals simple storage.retrieve. And what will happen is once this kicks out and is wrong, we'll actually get put into a Python shell. And now we can check to see some variables in here. Like if I see what expected is 15. If I try to run simple storage.retrieve, expected is 15. If I run simple storage, I'll see this is the simple storage contract. PDB is a really useful way to mess around and see, okay, well, what did I really go wrong? Why is my test failing? Another important flag is going to be -s. So you'll notice that no print lines actually get sent out when you're working with these tests. If you do -s, it'll be a little bit more robust in telling you exactly what's going on. And if we had any print lines, it would print the lines out as well. Everything that you can do with Brownie test actually comes directly from PyTest. So if there's some flag you want to use or some awesome debugger you want to use, you can use it with Brownie just by looking at the PyTest documentation. All the tools are exactly the same. All right, we're coming along fantastically. We have a script to deploy. We have some tests. We have our contract. This is great, but now we actually want to deploy to a testnet. How are we going to do this? Let's look at back how we did it with web3.py. Back in web3.py, to deploy this to a testnet, we just needed to add our HTTP web3 provider, which was our Infura account, and that was pretty much it, and add our address and our private key. In Brownie, our lives are even easier. Brownie comes prepackaged with a list of networks that it's already compatible with. You can see all of the networks by running Brownie networks list. Now, mine has a couple more actually because I've been playing around with this for a long time. But if you want to see all the different networks, you can look at this list here. Something important to note, is that there's a difference between the development networks and the Ethereum networks. Whenever we deploy to a network, we default to this development network. Any network that you see under this development section is going to be a network that is temporary. These are networks such as the temporary Ganache network that Brownie automatically spins up when we run any of the scripts we've written so far. So this is really important to note. Remember, anything in this development section is going to get torn down after it's deployed. However, the Ethereum ones are going to be our persistent networks. Anything under this Ethereum tab, Brownie is actually going to keep track of our deployments and keep track of everything in there. These networks under here represent persistent networks like mainnet, Rinkeby, Kovan, etc. Now in our web3.py, we used an RPC URL or an HTTP provider from Infura to connect to a testnet. We're going to use that exact same methodology here. So how do we actually get this RPC URL, this blockchain URL into our Brownie smart contract package? Well, one of the easiest ways is with an environment variable. So Brownie actually already knows that Infura is the thing and can look natively right away for Infura. Web3 Infura project ID and use our project ID from Infura. If we go to our project back in Infura and we go to settings, you'll see the project ID is a little bit different than the whole URL. It's just going to be this ID right here. We can then copy this and paste this right into our .env. Now that we have our Web3 Infura project ID directly in our project, if we do Brownie networks list, any network that Infura has access to, you'll see a little Infura in colons here. These are networks that Brownie will automatically know about if we're working with Infura. So we can see here that Rinkeby is one of these Infura keys. If we wanted to deploy to Rinkeby, we could then just run Brownie run scripts deploy.py and then select the network with -- network Rinkeby. Now we're going to get an issue here because remember, account 0 only works when Brownie works with a Ganache CLI. We have to use our actual private key here. And that's where some of those other versions of working with private keys is going to come into play. Sometimes I'll even add a get account function. So down here, we'll do def get account. And then in here, I'll just natively check. If we're working on a development chain, we'll use account 0. And if not, we'll use the method that pulls from our config. So we can check by saying if network.showActive equals development, then return accounts 0. Network is another keyword that Brownie actually has. This network keyword allows us to interact with different networks. Now, if it's not on the development network, we're going to pull directly from our config. So we'll return accounts.add config wallets from key. And instead of doing account equals account 0, we can just do account equals get account. Now if we run Brownie run scripts deploy.py network Rinkeby, it should pull directly from our config file. And great, we can actually see transactions being sent directly on the Rinkeby chain. If we pull up Etherscan, the Rinkeby Etherscan, and we take this transaction hash and post it into the Rinkeby Etherscan, we can see this transaction actually going through. We've deployed our simple storage contract and it's initialized to 0. Then we're going to go ahead and update it, and it gets updated to 15. Now, once we've deployed to a blockchain, you'll see our build contract will actually change. Our deployments folder will have a new deployment. Every time you deploy to a blockchain, Brownie will actually save that deployment so you can always go back and say, where did I deploy that, or what happened with that deployment? You'll notice that it's separated by chain ID. Remember, the chain ID of Rinkeby is 4. You'll also notice that none of our development deployments are in here. Again, anything that's in this development section isn't going to get saved to the deployments area. However, anything up here in these ones will get saved. And that's going to be really powerful because we can actually interact with contracts we've already deployed onto a chain. So let's go ahead and even add a new file in here called read value. This function is going to read directly from the Rinkeby blockchain, and it's going to read from a contract that we've already deployed. Remember, we did something similar in web3.py by using the address and the ABI. We're going to do the exact same thing, but in Brownie. So in Brownie, again, we're going to do from Brownie, import, simple storage, accounts, and config. We'll do def, read contract,